Hello there, and welcome to Life Beyond Seen, where curiosity drifts slower than snowfall, and science takes the quiet path through mystery. Tonight we're travelling to a place so remote that even silence seems to echo. A world at the bottom of the planet where light itself struggles to arrive. It's a landscape of blinding white and crushing cold, yet somewhere deep beneath all that frozen stillness, an ocean moves unseen. It's an ocean that hasn't touched the open air in millions of years, sealed away beneath a continent of ice. And despite its isolation, or maybe because of it, this hidden sea has become one of the most unsettling puzzles in modern science. What could possibly be living under Antarctica? What secrets does a body of water untouched since the age of dinosaurs hold? And why does the idea of it, so far away, so buried, so impossibly cold, make even seasoned scientists uneasy? Before we dive beneath that frozen ceiling, I'd love to know something simple. Where are you listening from tonight? Maybe you're wrapped in a blanket somewhere warm, or maybe you can feel the winter creeping at your window. Imagine, just for a moment, what it would feel like to be surrounded not by cozy air, but by endless ice pressing from every side. Down there, beneath several kilometres of frozen weight, time feels different. Light barely matters. The idea of up and down blurs into pressure and darkness. If you find this kind of slow exploration soothing, maybe give the video a like or even subscribe so this quiet corner of calm can find others who need a gentle journey through the strangest corners of Earth. Now take a breath. Let the day loosen its grip a little and follow me southward toward the edge of the world. Because somewhere under that endless whiteness, water is waiting. Antarctica doesn't often feel real. For most of us, it exists as a concept, a shape on a map, or a distant set of satellite images showing cracks and blue streaks of ice. Yet this continent is immense, larger than Europe, draped in a sheet of ice up to 4 kilometres thick. Underneath that frozen armour lies a terrain that no sunlight has touched in over 30 million years, a place that once held forests and rivers before it was swallowed by cold. Today it's a world locked away, but not silent. Beneath that ice, there are lakes the size of cities and rivers that flow unseen, all part of a hidden network that defies what we once thought possible. And at the heart of it all lies something so strange it almost feels mythic, a vast liquid ocean buried under an empire of ice. The existence of this ocean wasn't confirmed easily. For decades, scientists suspected there might be water beneath the Antarctic ice, but it wasn't until the late 20th century that technology caught up with curiosity. Radar pulses, seismic echoes, and satellite mapping began to reveal faint signals of liquid movement far below. What they found stunned them. Instead of a solid block of frozen land, the base of Antarctica was riddled with channels, caverns, and basins filled with water kept liquid by the heat of the Earth itself and the crushing pressure of the ice above. It was as if an entire hidden planet existed below our feet, one where rivers never saw the sky, and oceans lapped at ceilings of ice instead of clouds. When the first maps of this secret underworld were drawn, they looked more like star charts than geography. Dots representing subglacial lakes spread across the continent, hundreds of them, some connected by buried waterways stretching for hundreds of kilometres. One of them, Lake Vostok, lies beneath nearly 4 kilometres of ice and spans more than 200 kilometres in length. That's roughly the size of Lake Ontario, sealed away from the world since before the first humans stood upright. The thought of such a massive body of water existing in total darkness is enough to stir something primal in the imagination. Because where there's water, there's often life, and that's where fascination starts to turn into something deeper. Curiosity edged with unease. Life has a way of showing up in places we never expect. It thrives in boiling vents at the bottom of the ocean, inside acidic pools, even within radioactive waste. So the question naturally arose, could something be living beneath Antarctica too? If microbes or complex organisms managed to survive in that sealed, lightless environment, they would be unlike anything we've ever encountered. They would have evolved entirely isolated, shaped by pressure and darkness, breathing chemistry we can only guess at. For scientists, that's thrilling, but it's also unnerving, because studying such life means disturbing a system that's been untouched for millions of years, and we can't yet predict what happens when we open something that old. Imagine drilling down through nearly 4,000 meters of ice. Every layer represents a different age of the Earth, a frozen history of climate and air trapped in tiny bubbles. As the drill bores deeper, the temperature rises slightly, the ice becomes denser, and the pressure grows immense. Eventually, after days or weeks of careful progress, the instrument reaches a boundary where solid ice meets something new. A layer of liquid water, black, pressurized, ancient. When that first drop touches the sensor, it's like shaking hands with prehistory. What lies beyond it could rewrite our understanding of biology, or show us echoes of worlds beyond Earth. But it could also release bacteria or gases that haven't seen the surface since long before humans evolved. That tension between discovery and danger is what makes this hidden ocean so haunting. Scientists describe it as the last great frontier on our own planet. In a way, exploring beneath Antarctica feels more like exploring space than Earth. Equipment has to withstand temperatures that can freeze metal brittle, pressures that could crush submarines, and an environment so sterile that any contamination could ruin the entire mission. Even the smallest mistake, a trace of oil, a speck of foreign DNA, could alter the delicate chemistry of the lake below. So the teams who venture there prepare as if they're going to another planet. They build sealed drilling systems, sterilize every tool, wear suits designed to prevent even a single skin cell from falling into the water. When they finally pierce through the ice and send instruments down, it's not a rush of water that greets them, but a whisper of data, faint signals rising through kilometers of frozen silence. Those signals tell stories. They reveal currents beneath the ice, temperatures hovering just above freezing, traces of minerals that hint at interaction between rock and water. Some readings suggest that the hidden ocean isn't stagnant. It moves slowly, circulating like blood through the veins of the continent. This movement could carry nutrients from deep within the Earth, sustaining microbial ecosystems we've never seen. It could also link distant lakes together, forming a single, interconnected network of life beneath the ice. The more we learn, the more the line between Earth and alien world begins to blur. Because if life can thrive there, cut off from sunlight, surviving on chemical energy alone, then maybe life on other icy worlds, Europa, Enceladus, might not be so far-fetched after all. But there's another side to this story, one that feels less like wonder and more like warning. Antarctica's ice is not eternal. It moves, cracks, melts, and refreezes in cycles that shape coastlines and ocean levels across the planet. As the climate warms, that balance begins to shift. Satellite data shows parts of the ice sheet thinning faster than expected, glaciers retreating, and meltwater carving hidden tunnels through the ice. Those tunnels could eventually connect the buried ocean to the surface, releasing whatever it holds into the world above. It's a thought that keeps scientists awake even in their warm research stations, staring at data that suggests the boundaries between ancient and modern might not stay sealed forever. Part of what makes this hidden sea so mysterious is that we know just enough to be uneasy. We've seen hints of microbial DNA in samples taken from subglacial lakes, but we don't yet know what those microbes are or how they function. We've detected strange plumes of methane rising from cracks in the ice, but we're not sure if they come from geological processes or living organisms buried below. We've mapped the ice with radar and sonar, yet the images are still blurry, ghost-like outlines suggesting caverns and currents we can't fully interpret. Each discovery opens more questions than it answers, and every answer seems to whisper the same thing. There's more down there than we understand. In the quiet of Antarctic nights, when wind hammers the research stations and the temperature drops below -70, even the most rational minds admit to feeling the weight of that unknown. They're surrounded by darkness that goes on for months, working above a hidden ocean that might be teeming with unseen life. Every creak of the ice, every sudden crack or distant rumble reminds them that they're standing on a living system, slow, immense, and unpredictable. The ground beneath them is moving, shifting millimeters each day, carrying secrets that could change how we see our planet and ourselves. Yet it also feels like standing on the lid of a sealed vault, one we're only beginning to unlock. It's tempting to imagine what it looks like down there. Picture vast caverns lit only by the faint blue shimmer of bioluminescent microbes, icy walls dripping with mineral-rich water, slow currents weaving through corridors of stone and ice. Maybe there are mats of bacteria feeding on chemicals from the rock, creating strange ecosystems where sunlight has no meaning. Maybe there are tiny creatures with translucent bodies, evolved to sense heat or magnetic fields instead of light. Or maybe there's nothing at all, just water, ancient and sterile, holding the ghost of life that once was. Either way, it's a world utterly separate from ours, a parallel Earth existing in the same place but out of reach. For scientists, the fear doesn't come from monsters or myths. It comes from the realization that the boundaries we depend on, between ice and ocean, between life and death, between past and present, are thinner than we thought. The frozen ocean beneath Antarctica is a reminder that Earth still holds unknowns vast enough to humble us. Every drill core, every sample, every sonar scan is like tapping on the surface of a locked door, hoping it opens slowly and not all at once. And as we prepare to look deeper, to send machines even further below the ice, that mix of awe and apprehension only grows. Because beneath the white silence of Antarctica, the world is not asleep, it's waiting. Beneath the frozen expanse of Antarctica lies a secret so immense and so persistent that it challenges everything we think we know about this planet. When most people picture Antarctica, they imagine a continent of lifeless ice, a desert of snow stretching endlessly in all directions. The surface is hostile, its temperatures able to freeze steel, and its winds sharp enough to scour rock. Yet beneath that frozen armour, hidden from every human eye, lies an ocean that refuses to die. It moves silently beneath the ice, untouched by sunlight, older than the first city ever built, and colder than any sea we've sailed. For centuries it went unnoticed, existing as rumour, as mathematical possibility, as a whisper from radar signals that few believed could mean what they seemed to say. But now, through years of drilling, mapping, and patient listening, we know it's real. We know that beneath the world's largest sheet of ice lies not solid ground, but water, vast, restless, and alive in ways we can barely imagine. The story of how we found it doesn't begin with discovery so much as disbelief. Early explorers who crossed the edges of Antarctica in the 19th century saw only endless white, a continent locked in stillness. They assumed the ice went straight down to the bedrock, that the land below was frozen solid all the way through. When the first scientific expeditions arrived in the mid-20th century, their instruments told them something different. Radar waves sent through the ice sometimes bounced back in strange patterns, as if they were hitting smooth surfaces far below. At first, these reflections were dismissed as errors, the ice playing tricks on their machines, but as technology improved, the signals grew clearer. Under kilometres of compressed snow and glacial ice, there were vast flat plains that didn't belong to rock. Something was reflecting the radar perfectly, the way only liquid can. It took years to confirm what those signals meant. Researchers from the Soviet Union, the United States, and later Britain and Japan began to map the underside of the ice sheet using airborne radar. They flew back and forth across the continent, tracing the echoes. The resulting images revealed something astonishing. beneath Antarctica's frozen crust lay more than 400 interconnected lakes and rivers. Some were small, barely a few kilometres across. Others stretched for hundreds of kilometres, dwarfing anything above. The largest, Lake Vostok, became the focus of decades of study. Its surface sits nearly 4 kilometres below the ice, its volume so vast it could fill the entire Chesapeake Bay. And though sealed off from the atmosphere for at least 15 million years, it remains liquid, sloshing gently under the weight of all that ice. The pressure keeps it from freezing, and the heat from the Earth's interior adds just enough warmth to maintain a narrow balance between ice and water. When the realization sank in, scientists began to see Antarctica differently. It was no longer a simple mass of ice and land, but a living, breathing hydrological system. Rivers of meltwater snake through the base of the ice sheet, carrying sediments, nutrients, and perhaps microorganisms from one hidden lake to another. These rivers feed into larger basins, merging into subglacial seas that span entire regions. It's a world completely sealed from ours, where sunlight has never reached, and where time moves according to pressures and currents no human has felt. This hidden ocean system doesn't just exist in one place. It stretches across the continent like a buried network of veins, connecting the East Antarctic ice sheet to the west, pulsing with slow, invisible movement. Some of these channels may eventually drain into the Southern Ocean, releasing water that last saw the surface when giant sloths still walked the Earth. The ice above acts like a shield. It locks in heat, prevents evaporation, and creates a constant pressure that keeps the water liquid. Without that weight, the hidden lakes would quickly freeze. And yet, paradoxically, that same ice moves. It slides slowly toward the sea, bending, cracking, and reshaping the landscape below. This movement helps circulate the subglacial water, drawing fresh melt in one region and pushing older water out in another. It means the buried ocean isn't static, it's alive with change, even if we can't see it. From above, the surface of the ice appears motionless, but beneath it, rivers flow, sediments shift, and perhaps life stirs. Reaching this world, however, is a task that borders on impossible. The ice isn't just thick, it's pure, compressed to near crystalline hardness by millions of years of accumulation. Every layer represents a different age of snowfall, a frozen archive of the atmosphere stretching back almost 1 million years. Drilling through it requires precision that defies error. A single contaminated droplet from the surface could ruin an entire mission, introducing modern microbes into an ecosystem that has evolved in isolation for epochs. So scientists design their tools with the caution of surgeons. Every drill head, every pipe, every sensor is sterilized, sealed, and monitored. They use hot water drills that melt the ice rather than cut it, creating a clean path downward. It's not just engineering, it's restraint. The kind of patience required when you know one mistake could erase millions of years of untouched history. When the first probes finally reached these hidden lakes, the data they sent back seemed impossible. Temperatures just below freezing, yet liquid. Oxygen levels far higher than in surface oceans. Chemical gradients suggesting interaction with minerals from deep within the crust. And perhaps most intriguing, traces of organic material. Not proof of life, but the faint scent of it. These findings raise new questions. If the lakes beneath the ice are so rich in oxygen, why? One theory is that the enormous pressure of the ice causes microscopic bubbles of gas to dissolve into the water, creating a superoxygenated environment. That could support life. Strange, slow, microbial life adapted to eternal darkness and cold. Another possibility is that chemical reactions between water and rock at the base of the continent release energy, providing a source of fuel for living organisms that don't rely on sunlight at all. These are the same kinds of processes believed to occur on the icy moons of Jupiter and Saturn, which is why studying Antarctica's buried ocean could tell us not only about our own planet, but about life elsewhere in the universe. Still, every answer brings more unease. What exactly happens if we open these systems too far? If ancient microbes are released into the modern ocean, how will they react to our world? And how will our world react to them? Most may be harmless, long dormant, fragile under ultraviolet light. But we can't be certain. Evolution doesn't pause just because we weren't watching. Down there, in that closed ecosystem, life could have followed its own rules for millions of years. It could be built on biochemistry that diverged long ago from everything we know. When scientists collected the first samples from Lake Whillans, a smaller subglacial lake near the Ross Ice Shelf, they found microbial DNA sequences unlike any seen before. These organisms seem to feed on minerals and gases rather than sunlight, metabolizing iron, sulfur, and ammonia in total darkness. They were alive, active, and multiplying beneath ice that had sealed them in for millennia. The revelation was both thrilling and unsettling. It meant that life doesn't just endure, it adapts, it hides, it waits. There's also the geological side of the fear. That ocean, locked beneath the ice, contains vast stores of ancient carbon and methane. If the warming climate melts the ice sheets faster than expected, that trapped gas could be released, amplifying global warming in unpredictable ways. The ocean beneath Antarctica is not just a curiosity, it's a potential trigger in the planet's climate system. Scientists have found regions where the subglacial water is under extreme pressure, pushing upward against the ice above. If one of those reservoirs bursts, it could send torrents of meltwater racing toward the coast, destabilizing glaciers and raising sea levels far more quickly than we've prepared for. It wouldn't happen overnight, but in geological terms, and even in human lifetimes, it could happen alarmingly fast. This is why the frozen ocean terrifies scientists. It's not a monster in the dark, it's a mirror showing how delicate the balance of the planet truly is. Antarctica's ice has always been a kind of time machine. The deeper you go, the further back you travel into the planet's history. The ice traps air bubbles that record ancient atmospheres, particles that reveal volcanic eruptions, and isotopes that trace the rhythm of past climates. But beneath all of that, beneath the deepest layers, lies something older still. Water that remembers an Earth without ice caps, without humans, perhaps even without mammals. When researchers analyse the chemical composition of the subglacial water, they find signs of long isolation. The ratios of oxygen and hydrogen differ subtly from those in modern seawater, hinting at a separation lasting tens of millions of years. It's as if the hidden ocean is a message in a bottle, sealed and buried by time itself, carrying stories from a world before our own. Yet even as we uncover those stories, we can't help but notice how fragile the present one is. The same warming that allows us to study these hidden places also threatens to destroy them. The radar maps showing the shape of the subglacial lakes also reveal thinning ice above them. Some areas that were once stable are now melting from below, as warm ocean currents creep under the ice shelves and accelerate the loss. The hidden rivers that once flowed slowly beneath the ice are speeding up, carrying heat deeper into the continent. In the short term, this gives scientists new opportunities to study the subglacial ocean as meltwater pathways open naturally. But in the long term, it could mean the end of this ancient world. If the ice collapses entirely, the buried lakes will merge with the open ocean, releasing whatever they've held for eons. The line between ancient and modern will blur until there's no distinction left. For now, though, the frozen ocean remains sealed. Its surface, if we can call it that, is a ceiling of ice under unimaginable pressure. The water moves slowly, guided by gradients measured in millimeters per year. In some places it flows uphill, forced by the weight of glaciers. In others, it pools quietly in depressions, forming isolated basins where chemistry takes its own course. The darkness is complete. No sunlight, no photosynthesis, no day or night. Only the faint chemical glow of reactions between rock and water. The sound would be almost non-existent. just the slow crackle of ice shifting above, the faint hiss of trapped gases escaping into the liquid. It's hard to picture such a place without feeling a kind of reverence. Not fear in the cinematic sense, but the quiet, rational awe that comes from recognizing how much of our planet remains beyond our reach. And perhaps that's what draws scientists back, year after year, to this frozen edge of the world. Every new discovery beneath the ice seems to confirm two things at once: that Earth is far more alive than we imagined, and that we still understand very little of it. The frozen ocean beneath Antarctica isn't just a geographical curiosity. It's a reminder that exploration isn't about distance, but depth. We can travel to other planets, send probes beyond the solar system, and still find the greatest mysteries waiting under our own feet. Each radar scan, each data stream from beneath the ice adds another piece to the puzzle, but the picture never feels finished. The more we learn about what lies below, the more the surface world begins to look fragile, fleeting, temporary. Up above, storms whip across the ice shelves, snow erases footprints within minutes, and the wind howls like the voice of the planet itself. Down below, nothing moves quickly. The hidden ocean waits, patient as stone, indifferent to the passage of human years. It doesn't care who studies it or what fears it stirs. It has existed in silence longer than we have existed at all, and yet, now that we know it's there, we can't stop listening to it. Every echo from the radar, every vibration recorded by sensors in the ice, feels like a message from that dark water, one that says both come closer and keep your distance. Because what lies beneath the ice is not simply frozen history. It's the living memory of Earth itself, and it's reminding us that the line between discovery and disruption is thinner than the ice that hides it. Under the endless ice, there exists a world that time has refused to carry forward. It isn't simply hidden, it's preserved, sealed within layers so thick that the usual rhythm of decay and renewal has stopped. This world has slept through the rise and fall of continents, through the coming of mammals, through every flicker of human civilization. When scientists lower their instruments into that darkness, they are not just studying a landscape, they are stepping backward through millions of years into an era before our species existed. The air trapped in the ice comes from ancient skies. The sediments at the bottom of the subglacial lakes hold the chemistry of vanished ecosystems. Even the water itself is a relic, drawn from an ocean that existed before Antarctica became the frozen desert we know. Down there, beneath several kilometres of compressed history, the planet keeps its oldest secrets. Long before the ice, Antarctica was green. Fossilised wood, pollen grains, and leaf impressions tell us that it once supported forests dense enough to shade rivers and swamps. Dinosaurs walked there. Primitive mammals scurried under ferns, and the air was mild. Around 34 million years ago, continental drift pushed the landmass into its current position at the South Pole. Ocean currents shifted, and global temperatures fell. Ice began to spread, slow but unstoppable, smothering valleys and plains. The forests disappeared under snow, the rivers froze, and the continent transformed into the reflective shield that now regulates much of Earth's climate. The buried ocean beneath that ice is a remnant of the last liquid water that remained as the cold deepened. It's as if the planet tucked one piece of its warm past away, preserving it under a blanket of frozen time. For scientists studying climate history, this buried world is an archive without equal. The ice sheet itself contains annual layers of snowfall compressed into solid memory, but below that, in the sediments at the bottom of the subglacial lakes, lies the record of what came before. When cores are pulled from those sediments, they sometimes contain microfossils of marine organisms, tiny shells from when the area was connected to the open ocean. Other samples reveal traces of ancient soil, proof that parts of Antarctica were once ice-free and covered in vegetation. Each layer in those cores adds a line to a story that stretches back tens of millions of years, showing not only what the continent was, but what it might become again if the ice retreats. It's an unsettling symmetry. The ice hides a memory of warmth, and that memory warns us of a future that could melt it away. The temperatures and pressures in that buried ocean are like nothing we know on the surface. The water is liquid, but only just. Its salinity, pressure, and isolation make it a place where chemistry follows its own rules. Over millions of years, minerals leached from the surrounding bedrock have created a complex mix of nutrients and metals. Sulfides, iron oxides, and silicates drift through the black water like invisible dust, and where water meets rock, reactions occur that release hydrogen and methane, potential energy sources for microbes. If life exists there, it does so without sunlight, sustained entirely by the planet's internal heat and the chemistry of stone. That alone is extraordinary. Life powered not by the sky, but by the slow breath of the earth itself. The organisms that might inhabit this world would not resemble anything we know. On the surface, life evolved under the constant influence of light and atmosphere. It depends on oxygen and photosynthesis. Beneath the Antarctic ice, there is none of that. Any microbes there would have adapted to total darkness, extreme pressure, and scarce energy. Some scientists suspect they might metabolize iron or sulfur instead of oxygen, converting the chemical energy of minerals into life. Others think they could rely on the faint geothermal heat that seeps up from the crust. Whatever their strategy, these organisms would be survivors of isolation on a scale that defies comprehension. They would have evolved in a closed loop, their entire ecosystem built from the same materials recycled endlessly over millions of years. It would be a miniature planet complete unto itself. Finding evidence of such life is difficult. Every sample must be collected with precision that borders on paranoia. A single bacterium from the surface could contaminate a sample and erase the data. For that reason, when scientists drilled into Lake Willans and Lake Mercer, they used systems designed to remain sterile under pressure, melting their way downward with filtered heated water. The instruments carried sensors, cameras, and collectors built to withstand crushing weight and near-freezing temperatures. When they finally reached the liquid layer, the first readings suggested motion, slow currents, small variations in temperature, subtle chemical differences that hinted at interaction between the water and the sediment below. The samples brought back to the surface contained cells, simple, tiny, but alive. Genetic analysis revealed species unlike anything catalogued before, their DNA showing adaptations to cold, pressure, and lack of light. They weren't fossils, they were living remnants of an ancient biosphere still functioning in the dark. It's difficult to grasp what that means without stepping back from the data. For billions of years, Earth has been a planet of change. Continents drift, climates shift, species rise and fall. Yet here is a pocket of water that has remained cut off through all of it, sustaining a living system that never saw the sun rise. It is a direct line to the planet's deep past, a reminder that life doesn't just adapt to change, it hides from it, waiting for conditions to return. When we say the world that time forgot, it isn't metaphor, it's literal. The laws of evolution, decay, and extinction slow almost to nothing there. The creatures that survive under the ice are living in a time capsule, one that has drifted through eras while the rest of the planet moved on. The sediments at the base of the subglacial lakes tell an equally haunting story. They show layers of deposition that alternate between organic-rich mud and sterile mineral silt. Those layers may correspond to cycles of glacial advance and retreat, each representing a different climate regime. Some of the organic material appears to have been laid down by microorganisms that flourished when the ice thinned, suggesting that even small changes in temperature above can ripple through the buried ecosystem below. It hints that this world, while ancient, is not entirely disconnected. The ice above may seem immovable, but it breathes in its own slow rhythm, and the hidden ocean responds. This interplay between the frozen and the fluid creates a dynamic balance, a dialogue between surface and depth that has been going on for longer than humans have had language. When scientists model these interactions, they find something unsettling. The subglacial hydrological system can influence the movement of the entire ice sheet. If the water pressure increases in one region, it can lubricate the base of the glacier, accelerating its flow toward the sea. That means the ancient ocean below doesn't just record the past, it can shape the future. A pulse of meltwater deep beneath the ice can set off cascades of motion that eventually affect sea levels thousands of kilometers away. The forgotten world isn't dead, it's active, its slow cycles connected to the systems that govern the planet's climate. That's part of what makes it so unnerving. It's both ancient and alive, both sealed and powerful. The fear that accompanies this knowledge is not cinematic. It's quiet and persistent, a recognition that we are dealing with forces that don't care about our sense of time or control. Beneath Antarctica, processes unfold over millennia. The microbes that live there may divide once every few years. The chemical reactions that sustain them might take centuries to complete a single cycle. Yet these sluggish rhythms are part of the same planet that spins day and night for us. They are reminders that time on Earth is not uniform. It stretches and contracts depending on where you stand. Above the ice, a human life passes in moments. Below it, life measures itself in epochs. Some researchers call these subglacial environments analogues for extraterrestrial oceans. The icy moons of Jupiter and Saturn, Europa and Enceladus, are thought to have similar conditions. Thick ice crusts covering global oceans kept liquid by internal heat. The discoveries in Antarctica give scientists a model for what those alien seas might contain. If microbes can persist in the crushing darkness beneath the South Pole, then the odds of life existing elsewhere increase dramatically. But there's another, more sobering implication. If we can contaminate Antarctica's buried lakes simply by drilling into them, imagine what our machines could do to other worlds. The lesson is as much about humility as exploration. Sometimes to learn about life, we have to admit how easily we can disrupt it. The people who work in Antarctica often describe an eerie sensation when they stand on the ice knowing what lies below. The ground feels solid, but they understand that beneath their boots is not stone but a thin barrier separating them from a vast unseen ocean. It's a realization that changes their sense of scale. The white horizon around them becomes less a surface and more a fragile skin stretched over an ancient wound. They are not walking on land in the ordinary sense. They are walking on the roof of a different planet. Each creak of the ice, each low vibration carried through the frozen layers feels like a message from that buried world, a reminder that it's still there, waiting, unchanged. The samples that come back from those depths are handled with reverence. In sterile labs thousands of kilometers away, researchers open vials of water that have not seen the light of day for millions of years. They study the chemistry, the microbes, the isotopes, searching for patterns that might reveal the story of how life endures without sunlight. The findings are not always dramatic. Sometimes it's a slight variation in carbon ratios, a faint trace of nitrogen, a single cell visible under a microscope. But each detail adds to the picture. It tells us that this hidden ecosystem has been cycling energy, however slowly, for unimaginable spans of time. It suggests that the boundary between frozen and living is more flexible than we assumed. Even in places where the surface world would die instantly, Earth finds a way to keep a heartbeat going. There is a strange comfort in knowing that such persistence exists, even if it unnerves us. The buried ocean beneath Antarctica is not a threat in the ordinary sense. It won't erupt or swallow us whole. Its danger lies in what it reveals about the planet's memory. We like to think of time as progress, as movement forward, but this world shows that time can also stand still, holding on to the past until conditions change enough to release it. The sediments below the ice hold the chemistry of climates that may return. The microbes there embody forms of survival that could one day become necessary again if the surface grows harsh. They are the planet's insurance policy, written in water instead of stone. As exploration continues, the boundary between fear and fascination blurs. Each new mission dives deeper, each new dataset exposes more complexity. The deeper scientists look, the more they realize that what they're seeing is not an anomaly, but a pattern. Wherever there is isolation, life finds a way to persist. The world that time forgot may not be unique. It may be one of many pockets of ancient resilience scattered across the earth. Caves deep beneath mountains, sediments at the bottom of the sea, permafrost in the Arctic, all of them may hold echoes of earlier ages waiting to be rediscovered. Standing on the Antarctic plateau surrounded by white silence and endless wind, it's easy to believe that nothing could survive there. Yet below, life continues, indifferent to the surface storms. It doesn't know about continents, nations, or seasons. It simply endures, the same way it has since the world was warm and green. That endurance carries a kind of gravity, a quiet reminder that the planet is larger and older than any of our fears. When scientists speak of the world beneath the ice, their voices often soften. They know they're describing something that defies ordinary time, a piece of Earth that has refused to join the rest of history. It waits, as it always has, in the dark, patient and unchanged, until the ice above it moves again. And as they pack their instruments and prepare to return to the surface, they know that what lies below isn't finished speaking. It's only pausing, as it has for millions of years, before the next slow word in its conversation with the planet. Under all that pressure and silence, there is movement. It isn't fast or loud, but it's constant, the slow chemistry of survival taking place in a realm where sunlight has never reached. When scientists lower sensors into the hidden lakes beneath Antarctica, they aren't just measuring water temperature or salinity. They are listening for the faint signs of life, a shift in carbon levels, a trace of methane, a flicker of fluorescence under a microscope. Any of these could mean that something is alive down there, breathing without air, feeding without light, carrying out the daily work of existence in a place where days and nights don't exist. To stand on the surface above such a world is to feel a kind of double vision. One half frozen in the familiar white desert, the other trying to imagine a liquid darkness alive with unseen organisms. That tension between emptiness and abundance, between death and persistence, is what draws scientists deeper into the study of life in the dark below. The first samples pulled from subglacial lakes looked almost sterile. The water was crystal clear, nearly free of particulates, its chemistry balanced in a way that seemed incapable of supporting anything complex. Yet when researchers began to analyse it more carefully, signs of metabolism started to appear. There were faint concentrations of organic carbon, slight imbalances in isotopic ratios, and traces of gases that shouldn't have existed unless something was producing them. It was like hearing a heartbeat under layers of noise. As genetic sequencing improved, they found strands of DNA belonging to bacteria and archaea, unlike anything found in the surface oceans. Some appeared related to organisms that live near deep-sea vents, others to microbes found in polar ice. All of them shared one remarkable trait. They were adapted to darkness, cold, and scarcity. To survive in such a place, life has to make energy from what little is available. On the surface, sunlight drives photosynthesis, which forms the base of most ecosystems. In the darkness below Antarctica, energy must come from chemistry alone. Microbes there rely on chemosynthesis, a process that uses chemical reactions between minerals and water to produce food. In some parts of the subglacial ocean, iron and sulfur compounds react with oxygen to release energy. In others, hydrogen and methane provide the fuel. These reactions are slow, but steady. They support microbial colonies that can persist for thousands of years without any new input of energy from above. Each cell divides rarely, maybe once in a decade, but because the environment never changes, there's no rush. Evolution slows to a crawl. What exists there is less a population and more a living memory. Organisms perfectly suited to their frozen niche, with no reason to become anything else. The diversity hidden beneath the ice surprised everyone. When the first genetic surveys came back from Lake Whillans, researchers found more than 3,000 distinct species of microorganisms. Many were completely new to science. Some metabolized ammonia or nitrate, others broke down organic carbon left behind from earlier cycles of melting. A few even appeared to use tiny traces of sunlight that penetrated cracks in the ice during brief melt periods, although how they capture that energy remains a mystery. The discovery proved that subglacial ecosystems aren't marginal leftovers. They are fully functioning biospheres, connected through subterranean waterways that move microbes from one lake to another over geological timescales. In other words, beneath Antarctica there is not one isolated pocket of life, but a continent-wide network, slow, invisible, but very much alive. Understanding how these organisms persist tells us a great deal about the resilience of life itself. At near-freezing temperatures, biochemical reactions occur so slowly that most cells would be unable to function. To adapt, the microbes produce special proteins and antifreeze compounds that keep their enzymes flexible. Their membranes are rich in unsaturated fats that remain fluid in the cold. Some produce slime-like coatings that protect them from the crushing pressure. Others enter dormant states, repairing themselves only occasionally before returning to stasis. It's as if they have learned to live on the edge of non-existence, maintaining just enough activity to stay viable. The energy budgets of these organisms are so low that, on paper, they shouldn't be alive at all, and yet they are. Every analysis confirms it. Metabolism continues, however slowly, even after millions of years in darkness. There's an eerie beauty to that idea. While surface ecosystems rise and fall with the seasons, the subglacial world remains steady. There is no day or night, no winter or summer, only the quiet pulse of chemical reactions ticking away at the pace of minerals dissolving in water. If you could descend into one of those lakes, you would find an environment almost entirely still. The temperature would hover just below zero. The water would be heavy, dense, and silent. Sediment would accumulate grain by grain at the bottom, trapping whatever falls from the water column above. Flakes of bacterial colonies, bits of organic residue, traces of ancient rock. And somewhere in that sediment cells would drift slowly, feeding, dividing, or waiting. It's not the kind of life that moves or hunts or builds, but it's life all the same, and it's doing what life has always done, persisting against indifference. Some scientists call these organisms extremophiles, but that word doesn't quite capture their situation. Extreme implies rarity, a deviation from the norm, but under the ice this is normal. The conditions we find hostile are simply the only reality these microbes have ever known. To them, warmth and light would be fatal. They are tuned to the pressure and chemistry of their world as precisely as surface life is tuned to ours. That realization reshapes how we think about habitability. It means that life doesn't need what we consider comfort. It only needs stability, a reliable source of energy, and time. Lots of time. The frozen ocean beneath Antarctica offers all three in abundance. The connection between these hidden ecosystems and the surface world is fragile but real. Every few thousand years, glacial cycles cause parts of the ice sheet to thin, allowing meltwater from above to seep down into the lakes. That water carries oxygen and minerals, briefly refreshing the system. At other times, geothermal heat from below causes portions of the ice base to melt, releasing nutrients from the rock. In this way, the subglacial ocean breathes in slow motion, a single cycle taking millennia to complete. The microbes respond to these rare pulses of change, blooming slightly, multiplying for a few generations before settling back into dormancy. It's the most patient form of life imaginable, one that measures opportunity not in moments but in epochs. For researchers studying astrobiology, these findings have profound implications. The hidden ocean beneath Antarctica is the best analogue we have for extraterrestrial environments that might harbour life. On Jupiter's moon Europa, for instance, A thick shell of ice covers a global ocean warmed by tidal forces. Saturn's moon Enceladus has geysers that shoot plumes of water vapour into space, suggesting a similar ocean below. If microbial life can exist under Antarctica's ice, isolated for millions of years, then it could also exist on those distant worlds. Studying our planet's subglacial ecosystems becomes a rehearsal for searching beyond Earth. The same instruments designed to probe Lake Vostok or Lake Mercer could one day drill into the ice of Europa. The same caution against contamination will apply, because once again we'll be approaching a system that may have survived in isolation since long before we arrived to study it. Yet even as the scientific potential expands, so does the unease. The more we learn about life beneath the ice, the more we realise how easily it could be disrupted. A single, careless experiment could introduce modern microbes into an environment that hasn't encountered them before. Changes in climate could alter the delicate balance of temperature and pressure that keeps the lake sealed. If melting accelerates, these hidden ecosystems could be exposed to sunlight for the first time in millions of years. What would happen then is anyone's guess. The oxygen-rich water might react violently with surface chemicals, releasing gases or triggering blooms of bacteria that have no predators. The buried ocean might awaken in ways we can't predict, and whatever equilibrium it maintained in darkness could collapse. For the scientists who work there, this tension is always present. They are driven by curiosity but guided by caution, aware that every core sample taken from the ice, or droplet of water collected from below, is part of a world that doesn't belong to us. When they describe their findings, their language is careful, even humble. They speak not of conquest or discovery, but of encounter. To meet life in the dark below is to confront the vastness of biology's possibilities, to realise that what we see on the surface is only one expression of something much larger. The microbes under the ice are not anomalies, they are proof that the planet's capacity for life is far broader than our own experience of it. There are still many questions left unanswered. How did these organisms get there in the first place? Were they trapped when the continent froze, or did they evolve independently after isolation? How do they repair DNA damage without light-driven enzymes? What limits their population growth? Each expedition adds fragments of data, but the full picture remains out of reach. Some researchers think the subglacial ecosystems are ancient descendants of marine microbes, adapted gradually as Antarctica froze. Others suspect they may have been carried downward by meltwater during warmer periods, then sealed in place as the ice thickened. Either way, the result is a living link between Earth's past and present, an unbroken chain of existence stretching across deep time. Standing above that world, it's hard not to feel small. The wind howls, the snow blinds, and somewhere kilometres below, cells are dividing slowly in the dark, oblivious to the storms overhead. Their persistence makes our own achievements seem brief. The civilizations we build, the technologies we invent, even the instruments we use to find them, all of it will vanish long before their quiet metabolism stops. They are the real survivors of this planet, older than any lineage we claim, indifferent to everything but the conditions that allow them to keep living. That's the kind of thought that humbles even the most confident mind. We like to think of ourselves as masters of the earth, but beneath our feet, the simplest organisms remind us that the planet belongs to those who can endure it longest. As research continues, the boundaries of that endurance keep expanding. New drilling sites are being planned deeper inland, where radar has detected even larger bodies of subglacial water. Autonomous underwater vehicles are being developed to explore them directly, equipped with cameras and chemical sensors capable of operating for months in total darkness. Each new mission brings the possibility of encountering something unexpected. A new metabolic pathway, a new chemical signature, perhaps even multicellular life adapted to the crushing cold. It's not impossible. In the Arctic, scientists have found small worms and crustaceans living within glacial ice itself. If such creatures can exist near the poles on the surface, who's to say what might persist in the black ocean below Antarctica? The thought is both thrilling and unnerving, because every new form of life found there will challenge our definitions of where life can be and what it needs to survive. The deeper this research goes, the more personal it becomes for those involved. To spend months in the isolation of Antarctica, drilling into ice that predates humanity, knowing that the reward might be a few drops of water containing unseen life, is to experience a unique kind of perspective. It strips away the noise of the surface world. Down there, it's just you, the ice, and the knowledge that something beneath it is living its own slow, separate existence. When the instruments are pulled back to the surface and the samples are secured, there's often a moment of silence, not celebration, but respect. Because what's been touched is not just a sample of water, it's a glimpse into the persistence of life itself, a life that doesn't depend on our world at all. If you listen carefully to the data, to the quiet pulse of readings coming up through the ice, you can almost hear that other world breathing. Not loudly, not urgently, but steadily. It has been breathing since long before we arrived, and it will keep breathing long after we're gone. In that sense, the life in the dark below isn't a mystery to be solved. It's a reminder that the universe is full of endurance, that life finds ways to persist even in the absence of light, and that beneath the surface of certainty there is always another layer waiting to be discovered. Beneath the frozen mass of Antarctica, rivers run where no eyes can see them. They don't glitter, they don't roar, and they never meet the sky. Instead, they carve their way through darkness, slipping silently between rock and ice, connecting distant lakes and hidden seas into one vast secret circulation system. These are the hidden rivers of ice, the quiet plumbing of the frozen continent, the veins through which its buried ocean breathes. For years, even the idea of moving water under that much pressure seemed impossible. Ice should be solid, immovable, eternal. But as instruments grew more sensitive and satellites began to map the slightest variations in the surface, scientists realized the truth. The ice sheet is alive with motion, and beneath it, water flows constantly, shaping the land in ways we're only beginning to understand. At first glance, Antarctica appears lifeless, a perfect symbol of stillness. The winds whip across its plains, sculpting ridges of snow that look frozen in time. Yet from above, satellites have detected subtle patterns, shallow depressions that form and vanish over the course of years, regions where the ice seems to sag and then rise again. These changes are not random. They mark the slow filling and draining of subglacial lakes connected by narrow channels of meltwater. When a lake fills, the ice above it bulges slightly upward. When it drains, that bulge collapses, sending ripples through the ice sheet's surface like slow-motion tides. These movements, imperceptible to the human eye, tell us that the continent is not still at all. It breathes through water. The sources of that water are complex. Some comes from the pressure of the ice itself, which lowers the freezing point of water and causes the base to melt just enough to form a thin film. Some comes from geothermal heat leaking upward from the Earth's crust, providing a steady trickle of warmth that prevents total freezing. And some, more recently, comes from surface melt, a symptom of a warming climate that percolates downward through cracks and crevasses until it reaches the base. Once there, all of it joins a network that stretches across the continent, merging and diverging like blood vessels. The result is an entire hydrological system sealed off from the world above, where rivers can flow for hundreds of kilometers beneath 4,000 meters of ice, carrying with them sediments, nutrients, and perhaps even life. Mapping these hidden waterways requires a kind of indirect vision. Scientists rely on radar that can penetrate the ice, on seismic vibrations that echo through the ground, and on satellites that detect minute changes in gravity. Each method reveals a different piece of the puzzle. Radar traces the boundaries of lakes. Seismic readings outline the shape of buried valleys. Gravity measurements hint at variations in density that suggest flowing water. When combined, these datasets create a ghostly picture, an invisible geography of rivers winding beneath the continent. The scale is staggering. Some of these channels are as wide as major surface rivers, carrying enough water to fill entire reservoirs. Others are no more than trickles, thin threads that merge and split again, shaping the bedrock beneath the ice. One of the most remarkable discoveries came in 2007, when researchers identified a subglacial river system extending nearly 1,000 kilometers from the center of East Antarctica to the coast. It was nicknamed the Antarctic Artery. This single network connects multiple lakes, including the massive Lake Vostok, to the ocean. The flow is slow, measured in meters per year rather than kilometers per hour, but the implications are enormous. It means that water trapped deep within the continent can eventually reach the sea, carrying with it whatever chemical and biological material it contains. This circulation links the buried ocean to global systems, even if the connection takes centuries to complete. What happens under the ice doesn't stay there forever. To understand how these rivers shape the continent, imagine the base of the ice sheet not as solid but as a moving, deformable surface. The pressure from above forces meltwater into every available space, lubricating the contact between ice and rock. When the pressure builds too high, the water escapes along narrow channels, carving tunnels that guide the glacier's movement. This process, called basal hydrology, determines how fast the ice flows toward the sea. In some regions, a surge of subglacial water can cause glaciers to accelerate suddenly, sliding meters in a single day. When the water drains, the ice slows again. It's a hidden pulse that drives the rhythm of Antarctica's frozen heart. Every new measurement reveals more complexity. Some of the hidden rivers flow uphill, forced by the weight of the ice into gradients that defy ordinary gravity. Others loop back on themselves, creating circular basins where water collects before finding an escape route. In some places, geothermal hotspots beneath the ice create pockets of warm water that feed nearby lakes, sustaining them through periods when other areas freeze. The entire system operates like an underground ocean current, slow, interconnected, and surprisingly dynamic. And just like ocean currents, these flows can carry nutrients from one part of the continent to another, supporting microbial life in places that would otherwise be sterile. When samples are taken from the sediments deposited by these rivers, they tell stories of motion and connection. Grains of rock polished smooth by flowing water, traces of organic carbon carried from distant sources, and isotopic signatures that match those found in separate lakes hundreds of kilometers apart all point to the same conclusion. The rivers are moving material across the continent. In doing so, they blur the boundaries between isolated ecosystems. A microbe or molecule of organic matter released in one lake could, in theory, travel slowly through these hidden channels to another, linking distant environments into a single, sprawling biosphere beneath the ice. The dynamics of these rivers are also tied closely to the surface climate. When the temperature above changes, even slightly, it affects the pressure and flow below. A warmer ocean can thin the ice shelves at the coast, reducing the back pressure that holds the glaciers in place. That, in turn, alters the gradient of the subglacial rivers, accelerating their flow. Meanwhile, surface melting caused by warmer air can send pulses of water downward through crevasses, flooding the system from above. These changes can happen on surprisingly short timescales, months or years rather than millennia, and they ripple through the hidden network like distant thunder. For the scientists monitoring these shifts, each new data point carries both excitement and dread, because it means the under-ice system is responding to global warming in real time. In some ways, the discovery of these rivers has forced a redefinition of Antarctica itself. What was once thought of as a static block of ice is now seen as a dynamic landscape, constantly reshaped by the movement of water. It challenges the idea of ice as something lifeless and unchanging. The continent behaves more like a living organism, with circulation, respiration, and feedback systems that keep it in delicate equilibrium. Understanding those processes is crucial because they determine how the ice sheet will respond to future warming. If the hidden rivers accelerate and drain too quickly, they could destabilize entire glaciers, leading to sudden collapses and rapid sea level rise. In this way, the invisible water beneath Antarctica has global consequences. The exploration of these hidden rivers is one of the most difficult scientific tasks ever attempted. Every expedition begins months or years in advance. Equipment must be designed to withstand freezing temperatures, crushing pressure, and total isolation. Teams spend weeks travelling by snowcat or plane to remote drilling sites, where they build temporary camps on the ice. They work in 24-hour daylight during the Antarctic summer, taking advantage of every hour before winter seals the continent again. The drilling itself is slow, careful work, melting a narrow column through kilometres of ice without contaminating the water below. When the sensors finally reach their target, the data comes back in fragments, temperature readings, pressure variations, chemical analyses that must be pieced together like clues in a puzzle. What emerges from that puzzle is a portrait of movement so slow it almost defies comprehension. A drop of water released from melting ice in the interior might take hundreds or thousands of years to reach the coast. Along the way, it could pass through multiple lakes, picking up minerals, microbes, and chemical signatures that record its journey. When it finally escapes into the Southern Ocean, it carries with it a record of everything it has touched. In that sense, each droplet from Antarctica's hidden rivers is a message in a bottle from the deep past, telling us how the continent lives beneath its frozen mask. The more we learn, the more the boundary between fear and fascination blurs. The rivers represent both life and potential disaster. They nurture ecosystems that have survived in total isolation, but they also act as pathways through which trapped gases or ancient microbes could one day reach the surface. If warming continues, these channels could expand, connecting reservoirs that have been separated for millions of years. The sudden release of water from beneath the ice could lubricate glaciers enough to trigger massive calving events, sending enormous slabs of ice into the sea. It wouldn't happen overnight, but the chain reaction could accelerate in ways that are hard to predict. This is why scientists study the hidden rivers with such urgency, because understanding them may be the key to predicting how the ice sheet will behave in a warming world. There's a kind of quiet humility in this work. The people who dedicate their lives to studying Antarctica's hidden hydrology rarely see dramatic events. Most of their discoveries happen in numbers: a change in flow rate, a shift in pressure, a chemical anomaly that suggests movement thousands of meters below. But they know that those small changes are the first signs of something larger. The hidden rivers remind them that even the most frozen places are not truly still. Beneath the noise of wind and ice, the planet is always moving, always adjusting, always alive. If you could stand on the ice and imagine the rivers beneath your feet, you might feel something like vertigo. You'd know that under all that whiteness, water is flowing silently toward the sea, carving paths through rock and time. You'd realize that what appears eternal from above is, below, a world of motion and exchange. Every glacier, every ice shelf, every frozen plain is part of a network too vast to see, but too important to ignore. It's not just ice down there, it's the beating heart of a continent, pulsing slowly in the dark, and somewhere in that slow rhythm lies the next clue to how our planet breathes, how it remembers, and how it changes. Beneath the ice, the water is not empty. It holds traces of things that once lived, things that may still be living, and things that perhaps never belonged to the surface world at all. When scientists speak about the subglacial ocean, they often mention the samples they've pulled up through their long, sterile drills, the vials of ancient water that shimmer faintly under laboratory light, the cores of dark sediment that smell faintly metallic, the data that flicker on monitors showing chemical signatures unlike anything expected. They call them traces, remnants, anomalies. But in quieter moments, when the wind howls outside the research tents and the world above freezes solid again, they call them ghosts. Ghosts in the water, because that's what they seem to be. Faint echoes of life, whispering from a place where time has nearly stopped. When the first samples from Lake Vostok were analysed, the results defied expectations. The water, retrieved through layers of ice that had been sealed for at least 15 million years, contained fragments of DNA. Not one or two, but thousands. Some belonged to bacteria, some to archaea, some to small multicellular organisms that shouldn't have survived there at all. Many of these sequences were close to known species found in ocean sediments or hydrothermal vents, but others matched nothing in any genetic database. The scientists were cautious. Contamination from drilling was a possibility, and the purity of the samples had to be proven beyond doubt. But even after rigorous testing, some fragments remained unexplainable. They were too different, too distinct, as if they came from lineages that diverged from known life millions of years ago and evolved alone beneath the ice. To most people, fragments of DNA might not sound like much, but in the context of a sealed ecosystem, they are astonishing. Each strand is a record of something that once lived and metabolized, something that replicated its genes and left traces of itself behind. In an environment where light never penetrates, where temperatures hover below freezing and pressure could crush a submarine, these traces mean that life once found a way to exist, and perhaps still does. The sediments at the bottom of the subglacial lakes are rich with these signatures. They are layers upon layers of biological residue, compressed and preserved by the weight of the ice. When samples are warmed and analysed, the ghost signals flicker again, showing patterns of carbon isotopes consistent with metabolic activity. It's as if the organisms are still there, barely dormant, waiting for the slightest change to awaken them. In 2013, a team drilling into Lake Whillans found something more direct. They retrieved samples containing living cells, not fossils, not fragments, but living microorganisms capable of metabolism. Under the microscope, these cells glowed faintly when stained with fluorescent markers, proof that they were alive. Their DNA revealed thousands of species, including some that fed on ammonium, others that oxidized iron, and still others that produced methane as a byproduct of their metabolism. The water was oxygen-poor, dark and cold, yet these microbes formed a functioning ecosystem. They recycled carbon and nitrogen, building a food web entirely independent of sunlight. It was the first direct confirmation that life exists beneath the Antarctic ice, and it changed everything. The buried ocean was not a tomb. It was a cryptic biosphere, slow, ancient, and hauntingly active. But not all of the evidence fits so neatly into the framework of living biology. In some samples, researchers have found microscopic structures that resemble cells, but behave differently under analysis. They stain irregularly, their membranes are unusually thick, and they don't seem to contain the same proportions of organic compounds as known organisms. Some are coated in mineral films, as if biology and geology have fused together. Under electron microscopes, they look like the imprints of life. Shells without inhabitants, outlines left behind by processes we don't fully understand. They may be mineral precipitates that coincidentally mimic cell shapes, or they may represent ancient life forms whose chemistry diverged from ours long ago. Either explanation is unsettling. If they are non-living, it means that geology can imitate biology more convincingly than we thought. If they're living, or were, it means that life can take forms we barely recognize. These ghost forms appear alongside chemical anomalies that make the story even stranger. In the subglacial sediments, concentrations of methane are often far higher than expected. Methane can be produced by living organisms, but it can also arise from purely chemical reactions between water and rock under pressure. The isotopic ratios suggest both processes are occurring, overlapping in ways that are hard to disentangle. Some of the methane appears ancient, trapped in the sediment since before the continent froze. Some seems to be produced continuously. When scientists release these gases in the lab, they sometimes detect traces of carbon compounds that don't fit neatly into known biological pathways. It's as if the chemistry of the deep ice has been experimenting in isolation for millions of years, generating molecules that blur the line between organic and inorganic. The more the data accumulate, the more Antarctica's buried ocean begins to resemble a natural laboratory for prebiotic chemistry, the kind of environment that might have existed on the early Earth before life as we know it began. In that sense, the ghosts in the water aren't just echoes of the past. They may be glimpses of the process that first gave rise to life. The combination of pressure, heat, and mineral-rich water could have created conditions favourable to the formation of complex molecules, even primitive cells. If that's true, then the subglacial lakes are not only preserving ancient biology, they're reenacting its origins. The same processes that operate in the darkness beneath Antarctica might once have sparked life in the primordial oceans and could still be at work today, quietly repeating that experiment in the dark. Yet for all the fascination this brings, there is unease in every discovery. Every new drill hole, every new analysis carries the risk of disturbing something that has remained undisturbed for millions of years. Scientists have to balance their curiosity with restraint. They know that their presence changes the environment, even in small ways. Heat from the drills, trace chemicals from the equipment, microscopic particles of modern DNA. Any of these could alter the delicate chemistry of the subglacial water. The very act of looking risks erasing what is being observed. For that reason, many research programs now use autonomous instruments that can sample and test without breaching the sealed ecosystems. They record data remotely, transmitting it through fibre optic cables, leaving the water untouched. It's a compromise between knowledge and preservation, an acknowledgement that some ghosts are better left undisturbed. When scientists talk about the emotional side of their work, they describe a strange combination of awe and discomfort. The deeper they look into Antarctica's subglacial world, the more it feels like trespassing into a sacred place. The samples they collect are not just data, they're encounters with time itself. Each vial of water is a message from a period when the world was young and unrecognizable. Each microbe is a survivor from an age when continents were in different places and the atmosphere had different gases. Holding those samples is like holding a fragment of Earth's memory, something so fragile that it barely exists in the present. They call them ghosts not because they're supernatural, but because they carry the weight of everything that came before us. Some of the most haunting discoveries aren't the microbes or the DNA, but the isotopic signatures that reveal hints of biological processes that may have ended long ago. In some samples, scientists find traces of carbon that look like the metabolic leftovers of organisms that no longer exist. It's as if the water remembers their presence, even after their bodies have dissolved. These chemical shadows tell stories of ancient blooms, waves of microbial life that flourished when the ice was thinner or when geothermal activity was stronger. Then, as the environment changed, those organisms vanished, leaving only the faintest marks behind. What remains now is the residue of their lives, recorded in ratios of carbon and nitrogen that act like fingerprints in the dark. In one particularly striking discovery, researchers studying the sediments beneath the Whillans ice stream found evidence of sudden bursts of activity followed by long periods of dormancy. The chemical profiles suggest that the subglacial ecosystem isn't constant. It pulses, waking and sleeping in rhythm with the slow breathing of the ice above. When the pressure or temperature changes, the microbes stir, metabolize, reproduce, and then fall silent again as conditions shift back to stasis. It's a kind of living heartbeat, stretched over geological time. To the people studying it, it feels almost supernatural, a ghost pulse echoing through the depths, reminding them that life beneath the ice is never entirely still. There's another layer to this mystery, one that ties the ghosts in the water to the surface world. Some of the chemical compounds found in the subglacial lakes resemble those detected in samples from the icy moons of Jupiter and Saturn. The similarities are striking. The same ratios of methane to carbon dioxide, the same sulfur-bearing molecules, the same kinds of amino acids forming spontaneously in the presence of mineral catalysts. It suggests that the same processes shaping Antarctica's hidden ocean could be occurring elsewhere in the solar system. If that's true, then the ghosts in the water are not unique to Earth. They are part of a universal story, one in which life, or the potential for it, arises wherever water, chemistry and time intersect. For now, though, the ghosts remain confined to their frozen tombs. Each new expedition uncovers more traces, but never the full picture. The DNA fragments tell us that life has been there, but not how it looks or how it behaves. The chemical anomalies hint at activity, but not its origin. The mineralized structures mimic cells, but may not be alive. It's a puzzle that resists completion, as if the ice itself is guarding its secrets. The scientists continue their work, cautious and persistent, knowing that every answer leads to deeper questions. They'll keep drilling, sampling, analysing, trying to listen more carefully to what the water is saying. And somewhere down there, in the silence that has lasted millions of years, the ghosts continue their slow existence. Whether they are living microbes or only the echoes of ancient chemistry, they remind us that life, or something very close to it, is far more durable than we imagine. They are proof that the line between living and non-living is thin, and that the boundary between past and present is never as firm as ice might make it seem. When the researchers return to their camps, the vials sealed and the data stored, the image of those unseen organisms lingers in their minds, not as monsters or miracles, but as quiet presences that haunt the imagination, because even in the most silent place on Earth, the water still remembers. And what it remembers is everything the planet has ever been. Under the crushing weight of the Antarctic ice, human eyes are useless. Light can't travel that far, and even the brightest beams vanish within a few meters, scattered by crystals compacted over millions of years. Down there, it's a world of pressure and silence, a place where seeing gives way to listening. To explore it, scientists have built machines that don't just measure or record, but listen to the ice itself. They hear vibrations, echoes, whispers of movement and temperature, all the faint noises of a continent alive in slow motion. These machines are our only connection to the hidden world beneath our feet, the translators between human curiosity and the frozen planet's quiet language. The first of these devices was simple compared to what exists now. Decades ago, researchers would plant seismographs in the snow and wait. The instruments were crude, but they could sense when glaciers cracked, when ice slipped against rock, or when distant meltwater moved through unseen tunnels. Each signal appeared as a jagged line on a strip of paper, and each line hinted at motion. Over time, those early machines taught scientists something profound, that the Antarctic ice sheet, once thought static, was constantly shifting. Even when it seemed still, it was flowing outward toward the sea, grinding the bedrock below it into powder. Beneath that slow flow, water was moving, and the ice was responding. The continent wasn't frozen in place, it was breathing. Today, the instruments have evolved into something far more sensitive. Arrays of radar transmitters now send pulses deep into the ice, bouncing back echoes from layers far below. Each reflection carries information about what it hit: solid rock, liquid water, compressed ice, or a cavity filled with air. By timing how long it takes for the signal to return, researchers can map the internal structure of the ice sheet in astonishing detail. These maps look nothing like landscapes. They're more like medical scans, showing the cross-section of a patient so vast that it covers an entire continent. And in those ghostly layers, the radar reveals rivers, lakes, and deep troughs where the hidden ocean moves. The machines, in a sense, are eavesdropping on the conversations between ice and water. But not all of the listening happens from above. Some of the most remarkable instruments are the ones that operate within the ice itself. Autonomous probes that melt their way downward, carrying sensors, microphones, and cameras. These machines are designed to survive in the most unforgiving environment on Earth. They must withstand temperatures that can plunge below -80 degrees Celsius at the surface, and pressures that could crush steel once they reach the depths. They must also remain sterile, ensuring that nothing living from the surface contaminates the world below. Once deployed, they descend slowly, using jets of heated water or electrical coils to melt a narrow tunnel. As they move, they record data continuously: temperature gradients, acoustic signals, salinity, even faint chemical traces of life. Some of them never return. They melt their way down until the ice closes behind them, entombing them forever, silent witnesses left behind in the frozen dark. The technology behind these instruments is a blend of ingenuity and restraint. Every wire, every sensor, every power source must be designed for precision and longevity. Batteries freeze, circuits crack, and cables snap under tension, so the engineers who build them have to anticipate every failure before it happens. They use materials that can flex under pressure, coatings that resist freezing, and signal systems that transmit through kilometers of ice without distortion. The machines aren't built to conquer the environment, they're built to endure it. They must blend in, move slowly, and disturb nothing. They are guests in a world that never invited them. Some of the listening devices don't measure sound in the ordinary sense at all. They detect vibrations, the subsonic tremors caused by moving water, shifting glaciers, or fracturing ice. These signals are below the range of human hearing, but when sped up and converted into audio, they produce eerie tones, creaks, moans, distant booms that echo through the frozen continent. Scientists play these sounds back in laboratories thousands of kilometers away, listening to what the ice has to say. Each tone represents movement: a glacier sliding over bedrock, a lake draining beneath the surface, or the slow cracking of ice under stress. It's not just data, it's the sound of a planet adjusting itself. One of the most haunting aspects of these recordings is their rhythm. The ice doesn't move randomly, it pulses. There are patterns to the vibrations, cycles that correspond to tides, temperature shifts, and even the position of the moon. The subglacial rivers seem to swell and recede in response to the lunar pull, as if the hidden ocean beneath Antarctica has its own tide, one that echoes the heartbeat of the planet. The machines that record these rhythms have revealed something astonishing. Antarctica's buried waters are not isolated at all. They're connected both to one another and to the larger systems that govern Earth's climate. Every vibration, every subtle tremor is a reminder that what happens in the dark below influences the world above. To capture these signals, scientists often rely on arrays of sensors spaced across vast distances. They listen for synchronized echoes, a pattern detected in one location that matches another far away. These correlations allow them to trace the paths of subglacial rivers, to identify where water pools and where it drains. The data are fed into computer models that simulate how the ice flows and melts. It's a kind of detective work that never stops, because the system is always changing. The machines record more than movement. They record evolution. The most advanced explorers in this hidden world are the autonomous underwater vehicles, or AUVs. These are robotic submarines built to navigate the lakes beneath the ice, once the drilling teams open a small access hole. Each AUV is programmed to map the environment, collect samples, and return to its entry point without human guidance. They carry cameras capable of operating in total darkness, using short bursts of light to capture images of the lake bed and the water column. In those brief flashes, the cameras reveal scenes few have ever imagined. Walls of clear ice that shimmer like glass, clouds of sediment drifting in slow motion, and occasional clusters of microbial mats clinging to the rocks. The robots capture these images and then retreat upward, carrying with them the first visual records of a world untouched by sunlight. Every expedition that sends these machines into the ice is an act of patience. There is no room for haste. If something breaks, there's no fixing it. If communication is lost, the robot becomes part of the environment it was built to study. Many have been left behind that way, their final transmissions fading into static as they're swallowed by the ice. Each loss is felt deeply by the teams who built them, not just as wasted effort, but as a reminder of the limits of human control. The machines may listen, but the ice decides what it will allow them to hear. Despite the difficulty, the information they return is invaluable. By analysing radar reflections, acoustic echoes, and temperature gradients, scientists have created detailed maps of Antarctica's internal structure. These maps reveal features that were once unimaginable. Mountain ranges buried under kilometres of ice, deep valleys carved by ancient glaciers, and networks of water channels that wind across the continent like veins in a leaf. The precision of these maps allows researchers to predict where ice will flow, where it might collapse, and how sea levels could rise as the planet warms. Each new mission adds depth to this picture, and each new instrument becomes part of a growing chorus of machines listening to the frozen continent breathe. But listening to the ice isn't just about understanding its physical structure. It's also about understanding what lies beneath, the life, the chemistry, and the memory stored in the subglacial water. Some of the machines are equipped with chemical sensors designed to detect organic compounds or microbial activity. When these sensors pick up anomalies, traces of methane, slight shifts in oxygen, or fluorescence suggesting biological material, the data are relayed instantly to research teams waiting on the surface. Those moments are electric. For a few seconds, everyone involved knows they've touched something ancient and alive, even if only through numbers on a screen. Then the moment passes, and the long wait for confirmation begins. The scientists know better than to celebrate too soon. In this kind of research, certainty comes slowly, if at all. There's something poetic about the idea of machines that listen instead of see. They reflect a kind of humility, an acknowledgement that not all environments will yield to human eyes. We build instruments to extend our senses, to perceive the imperceptible, but even those instruments must adapt to the rules of the world they enter. In Antarctica, that means silence, patience, and respect for the cold. The robots don't crash through the ice. They melt their way in, one drop at a time. They don't shout, they whisper. They don't command, they listen. And in that listening, they remind us of a truth that's easy to forget. Knowledge isn't always about domination. Sometimes it's about stillness, about hearing what the planet is already saying. The scientists who design these machines talk about them almost affectionately. They give them names, paint small symbols on their sides, send them off like explorers into a realm that no human can enter. When they return, coated in ice and scarred by the journey, the researchers treat them like survivors. The data they bring back are precious, but so is the act of retrieval itself, the proof that communication with the hidden world is possible, however briefly. And when a machine is lost, it's mourned quietly. Somewhere under kilometers of ice, dozens of these devices rest in silence, their sensors still intact, their circuits preserved by the cold. In a way, they've become part of the environment they were sent to study, mechanical fossils waiting to be rediscovered by future explorers. Listening to the ice is an ongoing dialogue, one that will likely continue for decades. As technology improves, the signals grow clearer, the maps more detailed, the mysteries more focused. Yet even as our machines learn to hear better, the sense of mystery never fades. The ice still withholds more than it reveals. The echoes that return are faint, the chemical signals ambiguous, the biological traces elusive. It's as if the continent wants to be known only partially, keeping its deepest truths for itself. For now, the machines keep listening, patient and unblinking, capturing whispers from the depths that remind us of how little we truly know. And so the work continues. Each radar ping, each seismic tremor, each burst of static recorded in the darkness adds to the collective story of the frozen ocean beneath our world. The machines can't feel awe, but the people behind them do. They know that every line of data represents a connection between our small, temporary existence and the planet's vast, enduring systems. They know that somewhere under their feet, water moves through darkness older than humanity. And though the machines can't hear fear or wonder, those feelings echo in every human ear that listens to the ice alongside them. Because the deeper they listen, the clearer it becomes that the ice is not silent at all. It's speaking, slowly, patiently, in a language made of pressure and time, and we're only just beginning to understand what it's been trying to say. The moment the ice speaks back, it doesn't sound like a voice. It's not words or cries or anything that fits the way we usually define communication. It begins as vibration, a deep, low rumble that rolls through the ground, a pulse felt more than heard. Then another follows, and another, until instruments on the surface start to record patterns. The data flashes across monitors in distant labs, waves of frequency that mean almost nothing at first. But to those who have spent years listening, those waves carry meaning. The ice is responding. It's shifting, groaning, releasing energy stored for centuries. And if you know how to read it, the patterns form sentences. It's the language of glaciers, of water moving through rock, of pressure adjusting deep in the dark. This is what it sounds like when Antarctica speaks. Scientists used to think of the continent as silent, but now they know it's anything but. The ice sheet is constantly alive with sound, though not the kind our ears can easily hear. It creaks as it flows, it snaps as it fractures, it hums as it rubs against the land below. These sounds travel through the ice like signals, bouncing off layers, echoing through subglacial lakes and valleys. Every frequency tells a different story. Low rumbles reveal deep movements, sharp pops mark the birth of cracks. Faint hissing tones trace the flow of meltwater beneath. The machines that listen to this noise capture it all, and when scientists speed up the recordings, the result is astonishing. What was once a low vibration becomes a symphony, shifting chords of pressure and release, the continent itself singing in slow motion. Some of the sounds are familiar in a strange way. They resemble thunder, earthquakes, or waves breaking far away. Others are completely alien, high-pitched chirps, resonant booms, long, drawn-out groans that seem to echo forever. These noises aren't random. They correspond to physical events taking place beneath the surface. Ice sliding over rock, water draining from one lake to another, or vast sections of glacier flexing under stress. When combined, they create an acoustic map of motion. To those who study them, it's like listening to a living body. The ice has lungs, veins, a heartbeat. It exhales when it melts, inhales when it refreezes. Every sound is a sign of life, the slow, geological kind that spans centuries instead of moments. The first time researchers played back these recordings, they didn't know what to make of them. The sounds were eerie, sometimes beautiful, sometimes unnerving. One recording captured the collapse of a subglacial cavity, a sharp crack followed by a deep resonance that lasted several minutes, echoing through the ice like a bell struck in a cathedral. Another recorded the slow surge of a river beneath the ice, a steady crescendo that rose and fell over days as meltwater drained toward the sea. Some sounds repeated in regular cycles, suggesting tides or geothermal pulses deep below. Others seemed chaotic, unpredictable, like whispers from an ancient place that refused to explain itself. The technology that makes this listening possible has evolved rapidly. Modern instruments use arrays of seismometers and hydrophones placed across vast distances, synchronized to detect even the faintest tremors. These sensors are so sensitive they can pick up vibrations from the movement of microscopic bubbles trapped in the ice. When those bubbles burst, releasing ancient air sealed millions of years ago, the instruments register a tiny pop, a sound so small it would be impossible to notice without machines. Yet even those pops tell a story, revealing how gases migrate through the ice and how the structure changes with time. It's like hearing the frozen past slowly exhale. Sometimes the ice speaks in ways that startle even the scientists who've grown used to its voice. In 2018, a team studying the Ross ice shelf detected a continuous humming noise unlike anything recorded before. It wasn't the sound of cracking or melting. It was a steady vibration, resonating across hundreds of kilometers. The source turned out to be wind passing over the surface, causing the snow dunes to vibrate like the skin of a drum. The ice was literally singing. This natural resonance varied with temperature, wind speed, and pressure, allowing researchers to use it as a diagnostic tool. By listening to the tone of the hum, they could monitor changes in the ice shelf structure. When the pitch shifted, it meant something had moved. The continent was, in a very real sense, talking about itself. But not all the sounds are so benign. Some are warnings. When glaciers begin to accelerate toward the ocean, they generate seismic noise, a rising frequency of rumbles that indicate internal fractures forming within the ice. These rumbles precede massive calving events, where chunks of ice the size of cities break off and drift into the sea. Satellites can see the aftermath, but the instruments listening to the ice can hear the build-up long before it happens. They detect the stress accumulating, the crevices widening, the water pooling in hidden pockets. The ice, in its way, tells us what's coming. The challenge is learning to interpret its language fast enough to respond. There's a paradox at the heart of all this listening. The closer we come to understanding the ice, the more we realize how little control we have over it. The sounds we record aren't just the whispers of geology, they're also signals of change, sometimes of collapse. When a glacier groans louder or a subglacial river's pulse quickens, it can mean that melting is accelerating. The continent is responding to warmth from above, to human-driven changes in climate that reach even here, to the farthest corner of the world. The ice speaks back not because it chooses to, but because it can't help it. Every sound is a consequence, every tremor a reply. The planet is talking to us in the only language it has, vibration and movement, and what it's saying is urgent. For scientists in the field, these sounds become part of their daily lives. They camp on the surface, surrounded by endless white, and listen through their instruments. The wind screams across the plateau, but beneath that noise they can sense the deeper hum, the rhythm of the ice below. Some say it's comforting, like hearing the earth breathe. Others describe it as haunting, like standing above a sleeping giant and feeling its heartbeat through the floor. They know the sounds they record will be studied for years, each frequency analysed for clues about what lies beneath. But in the moment, standing there with headphones on, what they hear feels intimate. The planet isn't abstract anymore, it's present, alive, responding. In the laboratories where the data are processed, the scientists transform those vibrations into sound waves humans can hear. They speed up recordings of slow seismic events by factors of thousands, converting motions that take hours into noises that last seconds. When played through speakers, the result is astonishing. A soundscape that could be mistaken for an alien ocean. Low booms blend with high, crystalline tones. Waves of frequency rise and fall like breathing. Some recordings even have rhythm, repeating patterns that mimic the cadence of a song. It's difficult to listen without feeling something primal. Recognition, perhaps, or empathy. The ice is not conscious, but its voice evokes emotion all the same. The sounds of the ice have practical value too. They allow researchers to monitor areas that are otherwise inaccessible. When a crack forms deep within a glacier, it emits a specific acoustic signature. When water floods a subglacial tunnel, it produces a distinct rumble. By cataloguing these noises, scientists can identify events happening thousands of meters below without ever seeing them. It's a form of remote sensing that depends on patience rather than power. Instead of forcing entry, we wait for the ice to speak, and then we listen carefully. What's striking is how often the ice seems to respond to our presence. The heat from drilling, the vibrations from machinery, even the footsteps of researchers on the surface can trigger subtle reactions. In one study, sensors recorded a series of faint clicks whenever a team set up camp above a subglacial lake. The clicks stopped when they left. It was as if the ice had registered their weight and released tiny pockets of air in reply. The phenomenon was purely physical, yet it felt symbolic. The continent notices. It responds, not with anger or awareness, but with physics, the simplest form of dialogue imaginable. For many of the people who work there, this experience changes how they think about exploration. They come expecting silence and find conversation instead. They realise that the Earth is constantly expressing itself through sound and motion, and that we've only recently learned to pay attention. The ice doesn't just record the past, it reacts to the present. Every shift, every crack, every hum is data, but it's also a message. The more we listen, the clearer that message becomes. Nothing on this planet exists in isolation. Every glacier, every current, every vibration connects to everything else. The ice speaks back, not to warn or comfort us, but simply to remind us that it is part of the same system we depend on. There's a moment, late in the season, when the teams prepare to leave their camps and the machines fall silent. The antennas are packed, the instruments powered down, and the hum of generators fades into the wind. In that quiet, the scientists often pause. Without the machinery, the ice sounds different, deeper, softer, almost contemplative. It's as if, freed from the noise of measurement, the continent returns to its natural rhythm. They listen one last time before the engines start, before they lift off and leave the white expanse behind. And in that final moment, the ice seems to sigh, not from exhaustion, but from release. It's still speaking, always speaking, even when no one is there to hear it. Because the truth is, the ice has been speaking for as long as the Earth has had a voice. It spoke when continents drifted, when climates shifted, when species rose and fell. It carries the memory of those stories in its layers, compressing each age into soundless density. We're just the first generation with ears sensitive enough to hear it. And as we continue to listen to the cracks, the hums, the groans, the deep tremors of a world in motion, we begin to understand that the planet isn't silent after all. It's answering, and what it's saying, beneath the noise of our own making, is simple. I'm still here. I'm changing. Are you listening? It's impossible to study Antarctica for long without feeling something tighten in the chest. At first it's awe, the vastness, the silence, the sheer indifference of the landscape. But awe has a twin. It's the realization that this place, beautiful and ancient as it is, holds a kind of power that doesn't care about human limits. The deeper the research goes, the clearer that becomes. Every layer of ice is a record of time, and every record is fragile. Every new discovery on hidden lakes, living microbes, or subglacial rivers also opens another door to something darker. The understanding that what lies beneath can change everything above. The fear beneath the wonder isn't cinematic. It's quiet, rational, patient. It seeps in the way the cold does, slowly but completely. For decades, the story of Antarctica has been told as one of endurance and isolation. It's easy to think of the continent as separate from us, a sealed system at the end of the world immune to what happens elsewhere. But the truth is that nothing on this planet is isolated anymore. The hidden ocean beneath the ice, the one that moves silently through valleys and basins, is connected to the global system through physics and time. The fear begins there. Because what happens to that ocean doesn't stay buried. It flows outward in ways we can measure but barely control. The water under Antarctica is pressurized, ancient and heavy with gases trapped for millions of years. As the ice above it melts, that water is beginning to move. Slowly at first, then faster, and the world above is beginning to notice. The first warning signs came as subtle changes, shifts in sea level that didn't match predictions, the rapid thinning of ice shelves once thought stable. Then came the realization that some of these collapses were being triggered from below. Warm currents of water were finding their way under the ice, melting it from the bottom up. That process released more subglacial water, which in turn lubricated the glaciers, causing them to flow faster into the sea. It was a feedback loop, one that didn't care whether anyone was watching. In laboratories thousands of kilometers away, scientists began to model the consequences. They ran simulations showing what would happen if certain glaciers in West Antarctica gave way completely. The numbers were small at first, a few centimeters of sea level rise here, a few millimeters there. But the pattern was unmistakable. Once a tipping point was crossed, the collapse would accelerate, unstoppable, self-sustaining. The fear in those rooms wasn't theatrical, it was mathematical. The equations told them what their instincts already suspected, that the hidden ocean wasn't just a relic of the past, it was a weapon of change waiting to be drawn. The more the ice melted, the more the buried water would flow, and the more the glaciers would slide toward the sea. The Antarctic ice sheet holds enough frozen water to raise global sea levels by nearly 60 meters if it were all to melt. No one expects that in our lifetime, but the process has begun. The hidden rivers have awakened. The equilibrium that held for millions of years is shifting, and the planet is listening. The scientists who work in Antarctica feel this tension daily. They are surrounded by wonder, the beauty of the landscape, the mystery of the subglacial world. But beneath it runs a current of unease. Every discovery seems to carry a warning. When they find life under the ice, they celebrate, but quietly, because they know that life depends on isolation. If those ecosystems are exposed to the open ocean, they will die. When they find methane trapped in the sediments, they record the data carefully, because they know what methane can do. It's a greenhouse gas far more potent than carbon dioxide, and there are billions of tons of it sealed beneath the Antarctic ice. If even a fraction were released into the atmosphere, it could accelerate warming in ways no model can predict. The ghosts in the water are not just microbial, some are chemical, waiting for a chance to breathe again. In this sense, the frozen continent becomes a mirror. It reflects the best and worst of human curiosity. We dig, we measure, we analyze, and we marvel at the complexity of the system, and at the same time we edge closer to disturbing it. Each new probe that descends into the ice is both a triumph of engineering and a potential threat to the purity of what lies below. The fear beneath the wonder is not that the ice will attack us, but that we will destroy it simply by trying to understand it. It's the fear of irreversible contact, the moment when observation becomes interference, when science becomes intrusion. The line between discovery and contamination is as thin as the drill holes we melt through the ice. But there is another layer to the fear, one that has less to do with chemistry and more to do with scale. To study Antarctica is to confront time on a scale that makes human history feel irrelevant. The ice has seen everything. It recorded the rise of mammals, the wandering of continents, the formation and collapse of empires. It contains air that no living human has ever breathed. When researchers extract ice cores and analyze the trapped gases, they're not just studying data. They're touching ancient atmospheres, inhaling echoes of worlds long gone. It's awe-inspiring, but it's also unsettling, because in that comparison, our civilization looks small, temporary, fragile. The ice has survived mass extinctions and climate upheavals far worse than the one we are causing now. It will outlast us too, though in what form, no one knows. The fear grows stronger when scientists start to realize how little control they have over the changes already underway. Satellites show cracks spreading through ice shelves the size of countries. Seismic sensors record the groans of glaciers accelerating toward the sea. Some of these processes are irreversible. Even if global temperatures were stabilized tomorrow, parts of the Antarctic system would continue melting for centuries. The momentum is too great, the buried water too restless. What began as curiosity becomes dread. The planet is no longer the passive background to human progress. It's an active participant reacting to every action we take. The ice speaks back, and its reply is not comfort. It's consequence. There's also a more intimate kind of fear, one that doesn't come from models or data, but from experience. Scientists who spend months on the ice describe a sense of isolation unlike anything else on Earth. The white horizon stretches endlessly, and the silence becomes so complete that even thoughts seem loud. In that emptiness, the awareness of what lies below becomes almost physical. They know that beneath their boots are kilometers of ice, then water, then sediments that have been untouched for millions of years. They know that if the ice beneath them cracked, even slightly, they would vanish into a world no human has ever entered. Rationally, the danger is minimal. Emotionally, it's immense. The mind struggles to comprehend the scale of what's beneath it. The fear isn't of falling through, it's of realizing just how thin the line is between the known and the unknown. That same feeling carries over when they return home. The sounds of cracking ice, the data streams of pressure and movement stay with them. They begin to notice the parallels everywhere, in melting permafrost, in rising seas, in the shrinking glaciers of the northern hemisphere. Antarctica is no longer distant. It's present in every change happening across the planet. The buried ocean may be sealed in darkness, but its influence reaches into every coastline. That's the deeper truth behind the fear. What lies beneath the ice isn't just a geological curiosity. It's a force tied directly to the survival of the surface world. The more we disturb it, the more it answers. And yet, despite all of this, the work continues. The scientists return year after year, driven by the same curiosity that fuels their unease. They know the risks, but they also know that understanding them is the only way to prepare. The wonder never fades. The thrill of discovering a new lake, the first glimpse of living cells in a droplet of ancient water. But it's always accompanied by that shadow of apprehension. They've seen too much to feel pure excitement anymore. Every revelation carries a cost, every triumph a question about what will come next. The fear and the wonder are inseparable now, two sides of the same truth, that the planet is more complex, more alive and more precarious than we ever imagined. Sometimes, late at night, when the generators quiet down and the wind dies, the ice seems to settle, the temperature drops, the stars emerge, and the entire continent seems to pause. In that stillness, it's easy to imagine that the ice is listening too, not just to the machines or the people, but to everything. The slow turning of the earth, the distant hum of oceans, the faint rhythmic pulse of human activity far to the north. The scientists sitting in their tents, reviewing data by lamplight, become part of the same system they study. They are the surface thinking about the depths, the noise listening to the silence. And in that symmetry, the fear beneath the wonder begins to make sense. It's not terror of what's down there, it's recognition that the world we depend on is vast, fragile, and full of forces that neither love nor hate us. Antarctica teaches that lesson better than anywhere else. It shows that beauty and danger are not opposites but companions. The ice that holds the planet's oldest secrets is the same ice that could one day rewrite its future. The life that thrives in its buried lakes is both a symbol of resilience and a warning of how easily ecosystems adapt to isolation. The wonder that draws scientists to study it is the same force that drives them to confront their deepest fears of collapse, of contamination, of insignificance. The longer they stay, the more those feelings merge until they can no longer tell them apart. And so the work continues, not in defiance of fear, but because of it. The fear is what keeps the hands steady, what makes the procedures meticulous, what drives the calculations that might one day help predict the next collapse before it comes. It's not panic, it's reverence. The recognition that knowledge has weight and that curiosity unchecked can become destruction. The wonder opens the door. The fear makes sure it isn't broken down. Together they form the only honest way to study a world like this, one that's both breathtaking and indifferent, both beautiful and merciless. As the seasons turn and the research teams fly home, leaving their instruments to record in the silence, the ice continues to move. It groans, it shifts, it breathes, and somewhere beneath it the hidden ocean keeps flowing, carrying with it the stories of everything that's ever happened there. The scientists know they'll be back. They always are. Because for all the fear it inspires, Antarctica still holds something that no other place does. The feeling of standing at the edge of understanding, looking into the dark and realizing that the dark is looking back. For as long as humans have looked upward, they've imagined other worlds, some shimmering and distant, some imagined as mirrors of our own. It's a quiet irony that to understand those faraway places, we've had to look downward instead, beneath the thickest ice on Earth, into the black waters that have never seen the sun. The more we uncover beneath Antarctica, the more those alien landscapes begin to feel familiar. The frozen moon Europa, with its hidden sea beneath a crust of ice, Enceladus, spouting plumes of water vapour into space from a buried ocean, even distant Titan, where methane flows in liquid form under a dim orange sky. For decades these worlds seemed unimaginable, yet now the buried ocean beneath our own poles gives them context. The parallels are too strong to ignore. The fear and wonder that define our relationship with Antarctica are the same emotions that shape our search for life beyond Earth. When the first images of Europa's cracked surface were transmitted by spacecraft, scientists immediately saw something they recognized: patterns that looked like pressure ridges, the same kind that form when sea ice shifts on Earth. The idea that a liquid ocean could exist beneath that icy shell was revolutionary at the time, but what lay beneath Antarctica had already shown it was possible. Our planet proved the model. If heat from within could keep water liquid under kilometres of pressure here, then tidal forces could do the same on Europa. That simple connection changed the course of planetary science. Antarctica became a testing ground, a simulation of the alien. It offered a chance to practice listening to another world without leaving our own. Researchers began to study the subglacial lakes not just for their earthly significance, but for what they could reveal about life elsewhere. The parallels were uncanny. Both environments were sealed from sunlight. Both relied on chemical energy rather than photosynthesis. Both were shielded from radiation by thick layers of ice. The life forms discovered under the Antarctic ice, microbes that metabolize iron, sulfur, or methane, became models for what might exist on Europa or Enceladus. These organisms proved that life could persist without warmth, without light, without any connection to the surface. They showed that biology isn't limited by the boundaries we once thought essential. The realization was thrilling, but it carried a shadow. Because if life could exist so easily in the dark, then it might be everywhere. And if it's everywhere, then the universe is not a void. It's alive, endlessly, coldly, alive. That thought, like the discoveries beneath the ice, is both comforting and terrifying. Comforting because it means we're not alone. Terrifying because it means life is not special, that it's inevitable wherever the conditions are right, that it blooms and persists whether we see it or not. Antarctica forces that perspective onto everyone who studies it. To stand above its buried ocean is to stand on the proof that life doesn't belong to us. It's the planet's own creation, indifferent to the species that tries to understand it. That realization cuts deep. The microbes beneath the ice are alien, not because they come from another planet, but because they exist entirely outside our world of meaning. They live without witness, without history, without purpose beyond survival. They are what life looks like when stripped of story. Every probe we send into space carries echoes of the ones sent into Antarctica's lakes. The sterilized drills, the sealed instruments, the cautious protocols. All of it is born from lessons learned here. When we finally send a lander to Europa, It will drill through kilometres of ice much like those above Lake Vostok, using heat to melt a path and sensors to detect life without contamination. The difference is only distance. What we've practiced in Antarctica is the rehearsal for something far greater, the first conversation between worlds. Yet in that parallel lies another fear, the fear of repeating our mistakes. If we can disturb our own planet's hidden ecosystems through curiosity, what will we do to those on others? The same care that governs Antarctic exploration will have to guide every step we take beyond Earth. Because if the universe is filled with these buried oceans, each sealed and waiting, then every one of them deserves the same reverence. The more scientists learn about the mechanics of these icy worlds, the stronger the connection becomes. The ocean beneath Europa is believed to contain more water than all of Earth combined, held beneath ice that could be 20 kilometres thick. Enceladus, though smaller, has geysers that erupt from its surface, spraying material from its subsurface ocean into space. In those plumes, spacecraft have detected organic molecules, the same ingredients of life found in Antarctica's buried lakes. Even the chemical ratios are familiar: methane, ammonia, carbon dioxide, hydrogen. The universe is repeating itself, following the same patterns in places separated by billions of kilometres. What happens beneath the Antarctic ice might be happening right now beneath the crust of distant moons. The realization makes the Earth feel less like the centre of life, and more like a single instance in an ongoing experiment. For some, that perspective inspires hope. It means life is resilient, adaptable, and perhaps common. For others, it triggers the same quiet fear that accompanies every Antarctic discovery. Because if life can exist anywhere, it can also vanish anywhere. It can thrive unseen for eons, only to be erased by heat, pressure, or time. The buried ocean beneath our planet's south pole is stable now, but it wasn't always. There were times in Earth's history when the ice retreated, when the lakes drained, when the microbes that lived there may have faced extinction. The same could be true elsewhere. The universe might be filled with frozen worlds that once teemed with life, now locked in silence. When scientists look into the subglacial water and see those slow-moving microbes, they are looking into a mirror that shows both possibility and fate. The parallels go deeper than biology. The mechanics of ice itself, its fractures, its flows, its resonant hums, match the patterns observed on distant moons. The same stresses that cause Antarctica's glaciers to creak and groan likely shape the crust of Europa. When seismometers one day land there, they will listen for the same language we've learned to translate here. Each vibration, each echo, will tell a story about what lies below. The planet beneath our feet has already taught us how to listen. We know what a crack in the ice sounds like, what a subglacial river's movement does to the frequencies beneath the surface. Antarctica is, in a sense, our first conversation with an alien ocean, a dialogue that prepares us for the next. The fear that accompanies this realization isn't fear of the unknown, but of reflection. When we look at Europa, or Enceladus, we see the same physics, the same chemistry, the same persistence of life that exist here. The cosmos is holding up a mirror, and what it reflects back is unsettling. It shows us that Earth isn't unique, not in composition, not in potential, not even in fragility. The processes that keep the buried Antarctic Ocean alive are universal. If they can fail here, they can fail anywhere. The melting of our ice isn't just a local crisis, it's a lesson written in planetary terms. The survival of life, wherever it exists, depends on equilibrium. An equilibrium once broken doesn't return easily. When researchers compare the data from Antarctica to what's known about the icy moons, they see a pattern emerging. The environments that seem most hostile are often the ones that harbour the greatest resilience. Life, when it exists, hides beneath the surface, protected from radiation, insulated from change. It's the same instinct we share, building shelters, retreating indoors, seeking stability against chaos. Perhaps that's the most human thing about the hidden ocean, that its life forms behave in ways we understand intuitively. They withdraw from danger, adapt to scarcity, endure isolation. They are, in a strange way, reflections of us, not in form, but in persistence. The mirror doesn't just show the cosmos, it shows what we are made of. The scientists who dedicate their lives to these studies often speak of perspective. Standing on the Antarctic plateau surrounded by emptiness, they find it easier to imagine other worlds. The cold strips away the boundaries between Earth and elsewhere. The night sky stretches low and clear, and the line between stars and snow blurs. It feels, they say, like standing on another planet already. That sense of distance sharpens their focus. They know that what they learn here, the chemistry of the water, the structure of the ice, the behaviour of microbes, might someday guide the search for life across the solar system. They also know that what happens here could be a warning of what happens everywhere. If we can disrupt our own subglacial ocean through climate change, what hope do we have of protecting others? The mirror reflects both ways. There's something deeply humbling in that. The realization that every world, no matter how distant or frozen, is part of the same continuum of matter and time. The same laws govern them all. The same elements combine, separate and recombine, building life out of dust and water and pressure. Antarctica's buried ocean is just one expression of that universal chemistry, one version of a story playing out on countless worlds. Yet it feels personal, because it reminds us that we too are temporary, that we belong to the same cycles we study. The more we learn about these parallels, the less we seem separate from the universe. The fear beneath the wonder turns to something quieter, recognition. In the laboratories where samples from Antarctica are stored, the researchers sometimes hold small vials of water and think about the distance those molecules have travelled, from the ancient seas that once covered the continent, through eons of freezing, to this moment under human light. They know that within those droplets may be the same chemistry unfolding on Europa right now, unseen under alien ice. The connection feels almost sacred, not in a spiritual sense, but in a temporal one. Time doesn't separate worlds, it threads them together. The same processes repeat, the same ingredients recur, and in each repetition, something alive listens for warmth. The thought is beautiful, but it comes with its own unease, because if we are mirrors of other worlds, then our failures will echo too. The melting of our ice, the collapse of our balance, may serve as a warning written across the cosmos, a demonstration of how fragile even the most resilient systems can be. The hidden ocean beneath Antarctica is both an example and a prophecy. It shows that life can endure anything except indifference. It can adapt to cold, to pressure, to isolation, but not to carelessness. That is the final reflection the mirror offers. And so, as the scientists continue their work, drilling deeper, listening longer, mapping every vibration of the frozen continent, they are not just studying the past or predicting the future. They are holding a conversation with the universe. The buried ocean speaks through them, its lessons flowing outward like ripples. It tells of survival, of patience, of balance. It reminds us that we are part of the same system we study, that our curiosity and our caution must exist together. And as their instruments record the slow music of ice and water, they know that somewhere far away another ocean may be singing the same song. The mirror is wide, the reflection infinite, and the wonder, even with all its fear, never ends. The edge of the melt is not a line you can see. It isn't drawn across a map or marked by colour. It moves invisibly, creeping through ice, travelling under storms and darkness. It's the boundary between what was frozen and what is beginning to let go. To the human eye, the Antarctic landscape seems permanent, unmoved by season or year. But beneath that illusion, the edge is advancing. It moves in silence, carving its way upward through the ice shelves, downward through glaciers, sideways through cracks that widen by a fraction each day. The change is almost imperceptible until suddenly it isn't, until a slab of ice the size of a city breaks away from the continent and floats out into the Southern Ocean, turning white to blue to shadow. The moment passes quickly, but the consequences don't. The edge of the melt never retreats, it only waits, gathering momentum in the dark. The first signs appear deep below, where the hidden rivers shift their paths. Sensors buried in the ice start to record slight changes in pressure, small fluctuations in temperature that spread like whispers across the network. The water is warmer, only by fractions of a degree, but enough to change the physics of the entire system. A degree can mean the difference between solid and liquid, between stillness and movement. As the water warms, it begins to erode the base of the ice from below, carving tunnels that grow slowly then faster. It moves upward, finding weak points, exploiting fractures. In some places, it creates new subglacial lakes where there were none before. In others, it drains existing ones completely. The melt becomes a kind of intelligence, a patient and unstoppable force, rewriting the structure of the continent from within. At the same time, the ocean surrounding Antarctica is changing. The water that once protected the continent by forming dense, cold layers at the surface is now thinning and warming. Currents from the north carry heat deep beneath the ice shelves, melting them from the underside. This process is invisible to the satellites that watch from above, but it shows up in the instruments that listen to the ice. The frequencies shift, the tones deepen. Glaciers that once moved centimeters a year now slide meters in the same time. The sound of their motion is a low, continuous groan, the planet's slow exhale as pressure is released. Each surge of water beneath them is another reminder that even the thickest ice has limits. The edge of the melt doesn't move evenly. In some regions, it advances in sudden bursts. In others, it creeps forward with agonizing patience. It's a system driven by feedback loops. As melting accelerates, it exposes darker surfaces that absorb more heat. As glaciers thin, they let in more warm water. Every small change multiplies, feeding the next. Scientists watch these processes unfold through data streams and satellite images, but what they see isn't just numbers, is movement, alive and continuous. The maps update faster now. Each season shows new retreat lines. The ice shelves that once anchored the glaciers in place are collapsing one by one, and without them, the inland ice has nothing to stop it. It begins to flow outward, picking up speed, feeding the sea. For a long time, it was believed that the Antarctic ice sheet would melt from the top down, driven by rising air temperatures. Now it's clear that the real danger comes from below. The heat reaching the base of the ice doesn't come from the atmosphere, but from the ocean itself. In a sense, it's the planet's own body heat, rising from its depths, circulating through currents that humans have altered without meaning to. The excess warmth, trapped by greenhouse gases, doesn't stay in the air. It sinks into the sea, where it travels south, unseen and unstoppable. When it arrives at the frozen continent, it doesn't crash like a wave. It seeps in. It flows through underwater canyons, pressing against the ice, turning solid mass to liquid drop by drop. The edge of the melt isn't loud, but it's relentless. Once it begins, it doesn't stop. In some parts of the continent, the edge has already reached ancient ground. Sediment cores reveal layers of material that haven't seen the light of day for millions of years. They contain organic remains, trapped gases, fragments of rock that tell the story of older climates. Each layer uncovered by the melt is a page torn from Earth's archive, exposed for the first time and then erased as the water carries it away. The hidden ocean beneath the ice, once sealed in isolation, is beginning to reconnect with the global sea. Microbes that evolved in silence now drift upward into currents that circle the world. Chemical traces that have been locked away since before humanity existed are entering circulation again. The edge of the melt is not just physical, it's temporal. It's the moment when the past begins to flow into the present. Scientists trying to model these changes face an impossible task. The variables multiply faster than they can calculate them. Ice thickness, ocean temperature, salinity, wind patterns, geothermal heat, precipitation. Each one interacts with the others in ways that defy prediction. Every new discovery adds complexity instead of clarity. The melt moves through channels no one knew existed, under mountains that were only recently mapped, across fault lines that shift under pressure. Even the most advanced simulations can't keep up. The system isn't linear, it's alive, responding to itself in feedbacks that sometimes accelerate beyond control. The edge is unpredictable not because it's chaotic, but because it's precise. It obeys physics with perfect indifference, and physics has no interest in comfort. The fear this inspires among researchers isn't theatrical. It's the quiet dread of watching inevitability unfold in real time. They see the numbers rising, temperatures, flow rates, sea levels, and they know what they mean. The models that once described centuries of stability are compressing into decades. The places they've drilled, the lakes they've mapped, the glaciers they've crossed, all of it is changing faster than their equipment can record. Some regions that were once stable are now considered vulnerable. The hidden rivers beneath the ice are swelling, their paths shifting as meltwater floods new corridors. The ice shelves that once held back vast inland glaciers are thinning, cracking, breaking away. Each event is another line crossed, another threshold passed, and the edge keeps moving. It's not only the physical transformation that unsettles them, it's the realization of scale. The processes they study are slow by human standards, but fast in planetary terms. What they're witnessing is an acceleration that will echo for millennia. Once the glaciers start to retreat, their momentum continues long after the surface temperatures stop rising. The ice doesn't just melt, it collapses under its own weight, feeding the sea even in the absence of new heat. The changes they record today will keep unfolding long after their lifetimes. That knowledge is a burden. It means that the edge of the melt is not a moment, but an inheritance, a future already written into motion, and yet there's still wonder in it. The scientists who measure these shifts don't speak only of loss, they speak of revelation. The melting exposes landscapes no one has ever seen, valleys carved by ancient glaciers, mountains buried for millions of years, networks of frozen rivers turned liquid again. It reveals the hidden world beneath, the one that shaped the planet long before humanity arrived. The beauty of it is undeniable, even as it terrifies. The melt is destruction, but it's also exposure, the Earth revealing its own anatomy layer by layer. The researchers who witness it describe a feeling of reverence mixed with helplessness. They're watching the planet open itself, knowing they can't close it again. In the midst of all this, there's a growing sense that the edge of the melt is not confined to Antarctica. The same physics applies everywhere. Greenland, the Arctic, the glaciers of the Himalayas, they all respond to the same subtle rise in temperature, the same imbalance in heat. The processes are connected. What happens at the poles determines the fate of the oceans, and what happens in the oceans shapes the climate of every continent. The edge is moving outward, invisible but pervasive, rewriting coastlines, redrawing maps, rearranging the balance of water and land that has defined civilization since it began. The scientists understand this better than anyone, but so does the ice. The planet, indifferent as it is, has started to respond. At the coastal edges of the continent, the signs are visible even to the naked eye. Icebergs drift past research stations, carrying the compressed weight of centuries. The sea foams against fragments of glaciers that only weeks ago were part of the land. The air smells faintly of minerals and salt. The sound is different too. Less silence, more water. The edge of the melt has a voice, soft but constant. It's the sound of trickling beneath boots, of ice fracturing in the distance, of waves slapping against floating debris. It's the sound of transformation, of time shifting from solid to liquid. The scientists who stand there know that this moment will be studied for centuries to come. They collect samples, record data, and send it north through satellites and fibre optics. They speak carefully, knowing that each word might one day be read as history. But in private, they admit to something else, a feeling they can't quite name. It's not despair exactly, or even grief. It's a kind of recognition. The edge of the melt is what happens when the planet remembers its own warmth. It's the Earth returning to a state it has known before, long before us. We are the anomaly, not the ice. The melt is simply the world remembering itself. As they pack their equipment and prepare to leave, the edge keeps moving. They know that when they return, it will have advanced a little farther, reshaped a little more of the continent. The glaciers will have thinned, the lakes will have shifted, the data will have changed again. The work will continue because it must, even if the conclusions are already clear. The melt will not stop. The only question left is how much we will let it take. And as the last of the daylight fades, the ice glows faintly in the cold, a reminder of everything that's been lost and everything still to come. The edge breathes, quiet and unstoppable, waiting for no one. The stillness at the bottom of the world is unlike any other kind of quiet. It isn't just the absence of noise, it's the presence of something deeper, heavier, almost alive in its patience. Down here, sound dies before it travels. The wind can scream across the plateau above, but beneath the ice, that fury fades to nothing. The cold thickens the silence until it becomes physical, pressing against skin and mind alike. It's a silence that has lasted for millions of years, unbroken except for the faint shifts of water, the slow grinding of glaciers, and now, the distant hum of human instruments buried far above. It is the silence of endurance, of time stretched thin and unmoving. For the scientists who've spent years studying this place, there comes a point when the data stop feeling like numbers and start feeling like echoes. They've listened to the ice crack, to the water move, to the continent breathe. They've measured the melt and the flow and the hum of buried rivers. But when they speak about what lingers with them the most, it isn't the movement they remember, it's the stillness, the vast, perfect pause that exists beneath everything else. The kind of stillness that makes you aware of your own heartbeat, your own breath, the warmth of your body against the cold. It's the reminder that life, no matter how complex, is small compared to the scale of the planet's quiet. At the bottom of the world, time behaves differently. The clocks in the research stations keep ticking, but down below in the buried lakes and ancient sediments, time hardly moves at all. The microbes that live there replicate once every few months, sometimes only once a year. Chemical reactions proceed so slowly that a single molecule's transformation could span generations. The sediments shift at the rate of millimeters per century. Even the water circulation in the subglacial ocean operates on cycles measured in tens of thousands of years. To exist in this stillness is to be part of a rhythm so slow that the human mind can barely comprehend it. And yet it continues, unbothered by urgency, untouched by chaos. This is what makes Antarctica more than a place. It's a scale of existence. The stillness here is the opposite of emptiness. It's fullness, saturation. Every molecule of ice carries history. Every trapped bubble of air contains breath from a different epoch. The stillness holds everything, compressing it into silence. When scientists drill through the layers and release those bubbles, they can measure ancient carbon dioxide levels, reconstruct past temperatures, and even detect traces of volcanic eruptions that happened before humans evolved. But no measurement can capture the feeling of standing at the edge of that stillness, knowing that beneath your feet lies the unbroken memory of the planet itself. The stillness is deceptive too. To the untrained eye it looks eternal, but the instruments tell a different story. Beneath the quiet there's movement, glacial flow, shifting pressure, chemical reactions that never stop. The stillness is not absence, it's balance. It's the equilibrium point where all opposing forces cancel each other perfectly. Gravity pulls down, buoyancy pushes up, pressure compresses, temperature resists. The result is a tension so complete that it looks like peace. But equilibrium, once disturbed, can never return to exactly the same state. The stillness is fragile. Every vibration from above, every fraction of a degree of warmth, every molecule of gas that escapes into the atmosphere changes it in ways that can't be undone. The people who've studied the Antarctic ice long enough know this instinctively. They can feel the change, not just in data, but in mood. Each year the stillness feels a little thinner, the cracks run deeper, the rivers move faster, the hum beneath the surface grows louder. It's as though the continent is beginning to stir from its long rest. The fear that once lived in numbers now lives in sound. The ice speaks more often, and the spaces of silence between those voices grow shorter. The stillness that once seemed infinite now feels temporary, like the last breath before waking. And yet, it's still there. In the deepest parts, where no drill has reached and no light has shone, the stillness endures. There are places where the ice is so thick that even radar can't penetrate it fully, where pressure has compacted the crystals into a form of near transparency, denser than stone and older than language. The water beneath those regions moves so slowly that it might take millennia to circulate once. In those places, the planet is as close to timeless as it can be. Nothing disturbs it. Not warmth, not motion, not thought. It's as if the Earth has stored a piece of its own calm there, hidden away from everything that would alter it. Some scientists believe that understanding this stillness might be as important as understanding the motion around it. The stillness represents stability, the baseline of the planet's climate system. By studying it, they can see what balance once looked like. It offers a glimpse into what the Earth was before industry, before agriculture, before memory. The air trapped in those bubbles shows a world untouched by combustion or machines, a world breathing at its own pace. In that comparison, the contrast is stark. The stillness becomes a mirror, showing us what we've changed and what we've lost. There's a quiet reverence that settles over research camps when the day's work is done. The machines power down, the data is saved, and for a few minutes before sleep the noise fades. Outside, the wind moves across the plain, reshaping snow into patterns that no one will see again. Inside, the scientists sit in near silence, aware of the vastness beneath them. Some describe it as peaceful, others find it unsettling. It feels like sitting above an ancient mind that dreams in ice. That image isn't superstition, it's metaphor born from scale. The stillness makes you feel watched, not by eyes, but by history. It makes you aware that you're temporary, that everything human is temporary, and that the planet will go on long after memory fades. And yet, there's comfort in that realization. The stillness isn't hostile. It doesn't resist observation. It simply exists, constant and indifferent. It doesn't punish or forgive. It doesn't react to fear or hope. It's the neutral state of things, the way the world was before movement began. In that sense, the stillness at the bottom of the world is a reminder of what endurance really means. Not the act of surviving, but the ability to remain unchanged through everything else's change. The stillness doesn't care if it's being studied. It doesn't know that its preservation holds meaning for the species above. It simply continues, unaware that its silence is sacred. Sometimes, when teams prepare to leave for the season, they take one last moment before departure. The instruments are shut down, the tents packed, the generators quiet. They stand outside in the blue light that never quite becomes night and listen. There's always wind, sometimes distant cracking, sometimes nothing at all. But beneath that there's the hum, faint, low, nearly imperceptible. It's the vibration of the ice itself, the background resonance of a planet alive under its own weight. It's steady and patient and absolute, It's the sound of time continuing at a pace no human can follow. That's the true stillness, not silence, but persistence. When they leave, they know it will remain. It will outlast their instruments, their buildings, their species. It will hold the record of everything that has ever happened on this planet, layer upon layer, compressed into ice and stone. It will keep breathing slowly while the surface changes, while the air warms, while the oceans rise. The stillness doesn't end, it transforms. If the ice melts completely one day, that stillness will simply move, carried into the sea, diffused into the air, distributed across the planet that gave birth to it. The bottom of the world is not a place, it's a state of being. It's the reminder that even in motion there can be peace, even in loss there can be continuity, even in the loudest era of human noise there are depths that remain untouched. And so, as the planes lift off and the horizon fades into cloud, the continent returns to its rhythm. The snow falls again, erasing footprints. The wind rebuilds the drifts. The instruments buried deep continue to listen, though no one hears them anymore. And below it all, the ocean sleeps, dark and endless, turning in its slow cycle as it always has. The stillness remains at the bottom of the world, quiet, eternal, watching the passage of time as if it were nothing more than weather. The world above will change, the ice will rise and fall, but beneath it all, the deep calm endures, carrying with it the memory of everything that ever was. It waits, as it always has, for the next voice to listen, the next breath of warmth, the next moment when the silence is broken, and the earth, once again, speaks through its quietest place.